Right, exactly.
Good morning.
Nandi madam, very good morning.
Vinodini, good morning. How are you, ma?
I'm fine, madam. Thank you, madam. How are you?
Fine, pa. How are you?
Thank you, madam.
Can I try sharing my PPT once?
Organizers, please help, madam.
One minute, ma. I'll come back.
Good morning, madam. Dhanalakshmi madam, good morning. Good morning. எனக்கு கேட்கவே இல்லப்பா. Madam, unmute madam. Unmute madam.
Good morning, sir.
Good morning, madam. Good morning, madam. Good morning.
Madam, good morning. Is it
Good morning,
audible?
ma'am. It's audible.
Madam, good morning. Thank you.
Good morning.
Shall we start?
Yeah.
Or shall we start?
Three more minutes. 3 more minutes. Exact by 10 o'clock we can start. Vinodini madam, are you there, madam? Are you in?
I'm here, sir.
Okay, thank you, madam. Thank you,
You're
madam.
audible, sir.
Yeah, audible. Thank you, madam. Thank you, madam.
Am I audible, sir?
Yes, sir. Yes, madam. Yes, madam.
Good morning, madam. Vinodini, madam.
Good morning, madam. Nice to meet you on the virtual platform.
Yeah. Very happy to meet you, ma'am. As you are my senior.
Oh, really?
Yeah. In Algebra Sakti College, Dhanalakshmi. Chandrakala batch.
We should actually thank Puducherry branch for connecting us after a long time.
Welcome, Sandeepan sir.
Very good morning, sir.
Yes, sir.
Very good morning, Sandeepan sir, Vice President. Okay.
Oh, I'm waiting, sir. Okay.
Yes, sir.
Okay. Exactly by 10 o'clock we'll start, sir.
Okay, sir. Okay. Thank you.
Thank you, sir. Shall we start, madam? Yeah, shall we start?
Yes, sir.
Yes, sir.
Yeah.
Happy morning to one and all. On behalf of
Happy morning.
happy morning to one and all. Shall we
Happy
start,
morning.
sir?
Yes.
Good morning to one and all. On behalf of APTA Puducherry State Branch, I feel honored to welcome you all on this August occasion, one-day national webinar titled Women in Pharmacy Education and Mentorship, Inspiring the Next Generation Pharmacists. I take this privilege to invite all the dignitaries, respected Dr. Melvin General Umaker, sir, President, National Body APTI, Dr. Raman Dan, sir, Secretary, National Body APTI, Dr. Muttavarapu Venkataramana, sir, Vice President, Southern Region APTI, Dr. V. Sri Janardhanan, President, APTI, Puducherry State Branch, Mr. P. Seniyappan, Vice President, APTI, Puducherry State Branch, and all the EC members of APTI Puducherry State Branch and all the participants to this one-day national workshop. We'd like to
So please unmute yourself, everybody. Please, I request you to mute yourself. Yeah.
Now I would like to request Dr. V. Sri Janardhanan, sir, President APTI Puducherry State Branch, to give the presidential address.
Yeah. Thank you so much, madam. Thank you so much. Esteemed colleagues, distinguished speakers, honored chairpersons, and dear participants, good morning to one and all. It gives me immense pleasure to welcome you all to the national webinar on Women in Pharmacy Education and Mentorship, Inspiring Next Generation Pharmacists, which is organized by the Association of Pharmaceutical Teachers of India, Puducherry State Branch. And I honor to welcome Dr. Milan Jandra Umaker, President, National Body, Dr. Raman Dang, Secretary, National Body, APTI, and Dr. V. M. Venkataramana, sir, Vice President, Southern Region, APTI, and the distinguished speakers, Dr. C. Vinodini, Madam, Sri Ramachandra, Faculty of Pharmacy, Poru, Dr. C. N. Nalini, Madam, Principal and Head, C.L. Bade Mehta College of Pharmacy, Thorapakkam, Dr. N. Krishnaveni, Ma'am, Professor and Head, JSS Academy of Higher Education and Research, Ooty, Dr. Lakshmi, Ma'am, Dean, Chettinad Academy of Higher Education, and I welcome the chairpersons, Dr. Dhanalakshmi, Ma'am, Dean, Manapula Vinayaka Engineering College of Pharmacy, Dr. Manikandan, sir, Professor and Head, SRM, and Dr. Karthikeyan, sir, Professor, School of Pharmacy, Sri Balaji Vidyapith Deemed University, Professor Revati, Ma'am, School of Pharmacy, Sri Balaji Vidyapith Deemed University, and also I welcome Dr. Gana Anita, Secretary, APTI, Puducherry State, and the coordinators, executive committee members, and all other participants of various colleges. And I would like to welcome all the principals and head of the institutions of Puducherry Pharmacy Colleges. Once again, I extend a warm welcome to all of you to this esteemed national webinar on Women in Pharmacy Education and Mentorship, Inspiring the Next Generation Pharmacists, organized by the Association of Pharmaceutical Teachers of India, APTI Puducherry State Branch. And I wish you a productive, engaging, and enriching experience throughout this webinar. Thank you so much. Thank you so much for the opportunity. Thank you, madam. Please go ahead. Secretary, madam, please go ahead. Secretary, madam. Secretary, madam, please go ahead. Unmute yourself. Mute yourself. So unmute yourself. Anita, madam.
Sir.
Yeah, it's okay. Carry on, please. Please go ahead, madam.
Thank you, sir. Thank you for your wonderful presentation address. Now I request Mr. P. Seniyappan, sir, Vice President, APTI, Puducherry State Branch, to give the keynote address of this one-day national webinar.
Very good morning, respected dignitaries, esteemed speakers, faculty members, students, and all participants. As the Vice President of the APTI Puducherry State Branch, it's my great honor to deliver the keynote address for the one-day national webinar on women in pharmacy education and mentorship, inspiring the next generation of pharmacists, organized by APT's Pondicherry State Branch under the guidance of APTI Central. This event is a reflection of our collective commitment to recognizing and amplifying the role of women in pharmacy, a field that not only drives healthcare innovation but also nurture the future leaders. Women have consistently excelled as educators, researchers, and mentors, shaping the profession with their dedication and expertise. Mentorship, particularly, is a powerful tool for transformation. It bridges the gap between academic knowledge and professional success, fostering confidence, leadership, and resilience. Women educators and mentors play a pivotal roles in inspiring students to embrace challenges, pursue excellences, and lead with empathy and innovation. As a teacher and mentor, we have a responsibility to create platforms like this to highlight the achievements of women in our profession and to inspire the next generation of pharmacists to dream bigger and achieve more. This webinar is a step towards the goal, bringing together diverse perspectives and the experience to guide our collective journey forwards. The webinar is going to emphasize an advancement in modern analytical techniques for assuring quality of pharmaceutical, such as chromatographic, spectroscopic, and hybrid techniques are some of the breakthrough in ensuring the pharmaceutical quality. This webinar is going to gives women have been instrumental in advancing pharmaceutical research, particularly in quality assurance and regulatory sciences. I congratulate and thank the organizer for their efforts and thank all the participants for joining us in this important discussion. Together, let us continue to support, mentor, and empower the future leader of pharmacy. Thank you, one and all. Madam, it's over to you.
Thank you, sir. Thank you very much. Now I take the privilege to introduce our chairperson of the first session, Professor Dr. M. Dhanalakshmi Madam. Dr. M. Dhanalakshmi Madam is currently working as Dean, Professor cum Dean of SMVEC Pharmacy College, Madhukadipet, Pondicherry. She has completed her B Pharmacy in 2003 from Adiparashakti College of Pharmacy, Tamil Nadu, and M.Pharm from Annamalai University in the year of 2006, Chidambaram, Tamil Nadu. And she has completed her PhD in 2017 from Pacific University, Udaipur, Rajasthan. And her area of specialization is pharmaceutical analysis and quality assurance. She has owned one German patent, and she has received a research grant of 25 lakhs from BST WOSB, and she has published 45 national international papers in reputed international national journals, and she has received top 10 Women of Pondicherry 2024 organized by Society of Midwives India, School of Nursing, MTPG and RHS Puducherry. She has won an award, and she has guided 32 PG students and more than 50 bachelor students. And then she has attended more than 21 national conferences. She has been acting as an external examiner in Kapti University affiliated colleges in Telangana, and she is also acting as a subject expert for PhD programs in Sri Balaji Vidyapeeth University, Pondicherry. And she's also a member of professional bodies like IPA, the Indian Pharmaceutical Association, and she's also a life member of APTI. And she has taken various administrative roles like chairperson in BOS, SMBEC, Pharmacy College, examination branch, and PCI documentation for work for regular activities in SMBEC. With this, I hand over the session to you, ma'am, Dhanalakshmi ma'am.
Thank you, ma'am. Thank you for that. Thank you. Yeah, thank you for the introduction, ma'am.
Thank you,
Good
ma'am.
introduction too. Yeah.
Thank you, ma'am.
So it's my pleasure to invite resource persons Dr. C. Vinodini, Associate Professor from Ramachandra Faculty of Pharmacy. I'm very thankful for the presidents and vice presidents and secretary and APT members for giving me this opportunity to interact with all my seniors. Chance for me to interact with my senior. It's a day for me to respect my senior on this day. I thank God and all of us. Let me introduce about the resource persons of Dr. Vinodini ma'am. She's having the topic of separating the best from the rest, mastering HPLC. As the spectroscopy plays, chromatography and spectroscopy plays a very important role in chromatographic and spectroscopic analytical techniques. This plays a very, very important role for the young pharmacist students. Let me introduce about our madam profile. Madam has completed B Pharmacy in Adiprasati College of Pharmacy in 2000, and she has completed the M Pharmacy in Pharmaceutical Chemistry in 2002. Affiliated to MJ University, that is Madras Medical College, Chennai. And Madam has completed the PhD and Faculty of Pharmacy from Sri Ramachandra University, Chennai, in association with CLRI Adayar in the year of 2015. The research interest of the Madam mainly experienced in method development, method validations of analytical methods of various API formulation, herbal extract, and biological samples. And she is performing a qualitative and quantitative test analysis for raw materials, stability studies, drug product of long-term accelerated storage conditions. Madam also have a very nice hand of experience in operating knowledge of instrumentations of various HPLC, dissolution, FTIR, UV spectrophotometer. And she's experienced in chromatography data collection software using NPower and data interpretations. Quality by designs and green analytical approaches on antioxidants and cancer biologies. She is recognized and awarded in various process, such as the Best Paper Award of 6, and FDP organized and attended 34, workshop organized attended 60, conference organized and attended 33, conference paper presentation 53, and act as a resource persons 13, and quiz organized and attended 12, and webinars attended 49, reviewer in journals 3, and act as a pharmacy council of inspector for various colleges. And she has a course and model of Neptal 4 course area 1. And she also a member of Association of Pharmacy APTI. And she has received the Dr. Peter Fernandez Best Research Publication Award from the beloved Chancellor of Sri Ramachandra College in the year of 2023. And she has been published Q1 articles from the Science on the year of 2023. She had various responsibilities in the current college where she is working as an administrative committee from 2020 till now, and students advisor 2020 till now, research promotion committee member from 2020 till now, an International Yoga Day celebration 2022, and she is in charge for the timetable, regular academic timetable department from 2015 onwards, and she acted as a mentoring coordinator from 2020-21, and she acted as a vigilant committee, one of the vigilant committee member in COVID protocol monitoring in 2022, and she has been a GPAT coordinator from September 2022 till date, and she has done online education course in APTI in charge September 2022 till date. And she has a LMS model in charge online education training to new faculties and students enrollment for courses of UG and PG program. And she is a member of the health professional educations in the Sri Ramachandra College. Madam has various research activities. Mainly, she guided the UG B Pharmacy students from 2004 till date, 5 members, and PG Master in Pharmacy Master degree from 2007 till date, 26 members. And she is guiding the 5 members at present full part-time PhD scholar 3 candidates, and part-time 2 candidates, full-time 3 candidates. Madam has received the grants from various grant, young faculty research grant 6 and summer research fellowships 5. Total fund amount is 3,30,000. She has an extramural funding received as co-PI, principal investigator, sanctioned 53 lakhs in the year of 2021, and DST first 2020 application for PG college at level 0, advanced in pharmaceutical education and research publication index journals 36, published accumulating impact factors 14.05. And she has a patent of application number with the diametric prednium salts and its antibacterial and antifungal efficiency, published in the year of 2022. And really, it's a very immersive and happy to introduce Madam Dr. Vinodini ma'am to this section. I happily, heartily inviting you, ma'am, for this section.
Thank you, madam, for the very good introduction. I'm so happy that we have been connected with our UG college, and I must thank the Puducherry branch APTI for connecting us in this platform. So I think, can I start my session with all your permission?
Yes, yes, ma'am.
So, good morning and welcome to each and every one of you. I sincerely thank everyone for joining this session. And at the outset, I sincerely thank the President, APTA Puducherry, Sri Janardhanan Sir, for giving me this wonderful opportunity to share this platform. And also, I thank the Vice President for exploring us with the keynote address. And I thank the coordinator, Dr. Anita Madam, for coordinating this program. And also, I thank all the resource persons who are going to contribute their sessions today, and all the chairpersons. And with this, I just share my presentation slide. Can I share it now?
Yes, ma'am. Kindly, ma'am.
Is my presentation is visible?
Yeah. Yes, ma'am. Kindly.
Okay. From now, I think I can take a time of 1 hour to complete my session. So before I present the session, I would like to request Anita Madam to post the Google form, which I've already been submitted in the chat. So those who are present in the Google Meet as well in the YouTube streaming can please submit the form, not necessarily immediately, but you can parallelly fill up the forms as well at the end of the session, because the form is nothing but contains few questions which can make you to understand yourself about the concerned topic. So with this, I move on to the session by reflecting yourself. So let me ask a question. How familiar are you with chromatography? Because I should first understand the target level of audience. So in the Google Meet, if you are a beginner, just text 1. If you're an expert, text 5. I'm also interested to look into the chat. Just a few seconds, I may be knowing what kind of audience you are. If you're a beginner, text 1. If you're an expert, text 5. So if you are going to be a beginner for this session, I can assure that I'll do definitely justice for you based on the session progresses as well. If you are an expert, of course, I'm very happy to have you in this session. And you all agree to me that knowledge has no barriers and learning has no limitations. So even experts keeps learning every day and update themselves with the advanced technology. That is the actual objective of this platform APTI Puducherry has provided, to upgrade ourselves with the knowledge, skill, and the applications. So most of them are beginners. So let me start with few more interactive questions. It is for beginners. Which is most related to chromatography? So separation or identification? Which is the most related to chromatography? Separation or identification? Please text in a chat box. Okay, Vice President has replied as separation. Okay, mostly the answers are separation. You're right. So unless otherwise you separate, you cannot identify anything. So chromatography falls on to the separation process. And in which extract or a drug it has been first developed? Chromatography was first developed in the extract or in the drugs. Those who are well versed in the discovery of any analytical technique can answer to this. So Shivani has given me the answer, plant extracts. So most of them are extracts. Good to know that. The last question, what are the two phases involved in the separation? What are the two phases involved in the separation? Definitely we need two things, if anything, needs to be separated. So they're called as phases in chromatography. So I got answer like mobile phase. So mobile phase means you say it's one. Many of them have replied it is stationary phase and mobile phase, continuous phase and mobile phase. Of course, we need two phases, which is stationary and mobile phase for the separations. So to the content. So now look at this pictogram where I have classified the instrumental method of analysis, where you can see the predominantly the application towards the spectroscopy, and also you have some biological assays, hyphenated techniques, electrochemical methods, and miscellaneous thermal method of analysis, and X-ray diffraction, and so on. But the space occupied by the chromatography in the pictogram is really phenomenal. So there are different types of chromatographies that's been generated as years moves on, and still it is being updated to a proficient level of analysis in the pharma industry as well as in the other industries. So I believe that whatever may be the analytical technique, the learning should happen with the three levels of learning domains. As you all know that they are nothing but knowledge, skill, and attitude. Right? So always you should have an ability, or you should have a practice of learning any analytical techniques based on knowledge component, which is nothing but fundamentals or basic concepts, or it may be a terminology related to chromatography, or it could be a principle involved in chromatographic techniques, and so on. And skill is completely oriented towards how you get expertise in handling the equipment and what are the components that are present in the HPLC system. And finally, the attitude is nothing but after acquiring the knowledge and skill, how you are going to imply your experiences into action when you go and work in a pharma industry or any other opportunities in the pharmaceutical field. So when I move on to the objectives, now it has been strictly mandated by UGC that any lecture should start with a well-defined objectives, learning objectives, right? So I'm going to take this session into two parts. Probably the first part will be onto the theoretical aspects, where you'll be learning onto more towards knowledge components, which means how to define chromatography, what are the scopes, what is the principle of mechanism involved in that, and different types of chromatography, and how you're going to connect the hydrophilicity and hydrophobicity towards the separation process, and also the different elution modes. The part 2 will be probably focusing towards the instrumentation and applications of this technique. So moving on to the, looking back into the history of chromatography, and many of them said it has started with the evolution with the plant extracts, where you can see the scientist Tesvet, who has developed this technique, column chromatography, by packing the column with calcium carbonate as an adsorbent, which is actually a stationary phase, and also the mobile phase is petit ether, which is a flowing phase, otherwise called as eluent, where he separated the chlorophyll, which is actually green color, and it has been separated into two different bands, red and black. That's how the evolution of the chromatography started in the year 1906. We are just 100 more years back for this evolution, and that's how it has started. And later on, when you look into the expectation that has been arrived in the field of researchers and in the industry or in the academic, that someone needs a quantitative application from a technique, and someone needs a very good effective separation and different separation processes or extraction techniques, and someone needs to isolate and purify a chemical constituent or analytes which is present in a mixture. So chromatography is a separation techniques, and it is expected to fulfill the analytical part as well as purification, isolation, qualitative and quantitative are the expectations. So thereby you can see after 50 years of the the evolution, Professor Joseph Kirkland, who has developed HPLC in the year 1967, which is going to fulfill all the requirements of the researchers in the field. So he is being called as father of HPLC. So looking at the principle of liquid chromatography, as you all know that we needed two phases. One is stationary phase, which is being packed into the column, and other one is the mobile phase, which is being flowing into the column, and thereby you can separate the mixture of components by collecting it into and later on detecting it with a suitable detector technique. And what is the final outcome of this technique? It is nothing but the mixtures can be separated, which in turn can analyze or identify or purify or quantified. So that's how the outcome of chromatographic technique can be arrived at. So when you look into the types of chromatography, broadly you can classify them into liquid chromatography, gas chromatography, and supercritical fluid chromatography. So that varies, depends on the type of the mobile phase that you employ into the separation process. Say for example, if it is a liquid chromatography where liquid is employed, and gas chromatography, inert gases are employed, and just a decade back, there's an evolution of supercritical fluid chromatography where the supercritical fluids are employed as a mobile phase, just like carbon dioxide, ethane, or xenon. So what is the specialty of this supercritical fluid chromatography? The fluids are having the in-between properties of a liquid and gas. They have the intermediate property of a gas and a liquid in terms of its solubility and diffusivity. So this is one kind of chromatography, but mostly the employed chromatography is liquid chromatography. And now we have to understand why HPLC is very important, because this particular technique facilitates the simultaneous analysis. We all know that nowadays most of the drugs that are available in the market are fixed dose combination drugs, where you have more than one drugs in a combined dosage form. So it is need to develop a method where the many components that are present in analyte can be estimated with the highest degree of accuracy and precision. And HPLC gives a better separation compared to the other levels of chromatography. And it is highly sensitive in terms the detectors employed in the HPLC can detect even a change in small concentration of your sample, and thus gives the sensitivity to the method, good repeatability, and you require even a small sample size, and there is no need for any specific conditions like GC over here. You can operate the HPLC in a moderate analytical condition, and it is very easy to fractionate the sample and purify. And it does not involve any destructive detectors, which means the detectors are widely employed as a bulk property or a solid property, and it is universally accepted detectors employed in HPLC. For these many reasons, HPLC is quite being considered as a cornerstone of the many of the industries, and even in pharma industry, it is assumed as a backbone of the pharmaceutical industries in terms of research as well as in the routine quality control analysis. So as I said, apart from pharmaceuticals, the applications extended much towards biochemical, food products, industrial chemicals, forensic chemistry, environmental field, and even in a biological sample estimations in terms of clinical medicine. So how does the separation happens in a column when it is packed with the material? So you can see here, there are two analyte, one is red, the other one is blue, which has been flowing into the column with the help of the external mobile phase. So the separation happens because these molecules are not same. Even though they are present in the mixture, they vary slightly in their polarity. So this makes the difference in the elution pattern. So when these molecules travels into the column, you can see that one is traveling faster than the other, which means red is traveling faster than the blue. So this difference highly makes the separation difference in the chromatogram that is obtained as an output. So the one which has the stronger interaction, say for example blue here, so which will adhere to the stationary phase for a longer time compared to that of the one which has a weaker interaction, say red. So the one which has stronger interaction in the stationary phase will be eluting later on, and the one which has a weaker interaction with the stationary phase will elute in an earlier time. So on the other hand, you can look into the separation that the one which has stronger attraction towards the mobile phase will be eluting first, and the one which has weaker attraction towards the mobile phase will be eluting later. You can understand in terms of its relative affinity towards the stationary phase or towards the mobile phase. So this becomes the basic fundamentals in the separation mechanism of whatever may be the type of HPLC we are going to discuss in the next few slides. So some terms are very important to understand the fundamentals of chromatography. So you can see here, a chromatogram is nothing but the output. So generally, any technique will be called by the suffix graphy. So chromatography is the technique, and chromatogram is nothing but the output or signal or the response you arrive out of an analysis. And chromatograph, when any term that ends with graph, it is nothing but a instrument, right? Chromatograph is an instrument, chromatography is a technique, and chromatogram is the response that you get out of a instrument. And mobile phase is nothing but a flowing solvent, as you all know. It can be also called as an eluent. And stationary phase is the other phase, important phase, where a separation happens, and it's nothing but different materials packed onto the column. And then peak is nothing but the visual representation of a chromatogram. Let us going to talk about how the peak should be and what are the complications if you're not getting a normal peak later on. And retention time is nothing but the time taken for a peak or a substance or an analyte to reach the detector. So it is expected that 50% of the sample should reach the detector, and thereby the retention time will be calculated from the chromatogram. And qualitative aspect is nothing but how the HPLC is going to helpful in identifying the compound. And it does not stop by identification only, it also should extend to the quantification level. So that is called as quantification. And when we move on to the different separation modes in HPLC, you can use HPLC for separating the analyte using a normal phase elution or reverse phase or ion chromatography or size exclusion or affinity chromatography. So when you move into the aspect of reverse phase mode, you can see that there is a presence of non-polar stationary phase and polar mobile phase. This is a condition that is applicable for a reverse mode. This combination is called as a reverse phase mode, and whereby you can see the silica is being attached or combined with of a non-polar phase, C18H37. It is nothing but extension of a carbon chain in a silica. So silica is basically a polar compound. When you extend the silica by attaching these non-polar substituents, so it becomes a non-polar characteristic. So when you use a non-polar stationary phase and polar mobile phase, you can run a reverse phase chromatography. There are other types of columns are available like C8, C4, phenyl type, TMS, and cyano type. So C18 is nothing but octadecyl column. ODS stands for octadecyl silane column, which can separate most of the polar compounds. So you all know that drugs are all polar mostly, which is available in the market. So when you adopt this reverse phase chromatography, being a polar drug, it will have least affinity towards the stationary phase but has more affinity towards the mobile phase. So thereby what happens, your elution time will be reduced, so the drug will absorb for a shorter time and then it gets eluted in a shorter runtime with the mobile phase. So that is the one biggest advantage of going with reverse phase in terms of a polar component. And how do you connect the hydrophobicity to the separation? So let us take two examples here. One is with the carbon chain and the other one is a aromatic compound. So both are considered as hydrophobic groups because the carbon chain can extend to any level, as well as aromatic compounds are hydrophobic. And there are also few compounds you can see here with the polar groups like carboxylic acid, amino group, hydroxyl group. So we assume them as a hydrophobicity is weaker here because they are all polar compound where hydrophilicity will be more. Then coming to the mobile phase, generally the water and normal distilled water cannot be used. So HPLC grade water, or you can replace water with that of the buffers. So when you use buffers, various parameters needs to be considered, like pH of a buffer, concentration of a buffer, and what kind of buffer you use, what is the pK of the buffer that you are going to employ into the method. And along with this polar solvents, there is also a mixture of organic solvents used like methanol, acetonitrile, THF, and all these organic solvents should be compulsory of HPLC grade, which is the purest form of the solvents. And let us take an example to connect retention time and hydrophobicity, where you can see I have taken two examples. One is the very polar group where it is phenol, and the other one is the non-polar, which is having carbon chains. attached to the structure. So this particular compound, the second one, will have stronger interaction to C18, because I said that number 2 compound is non-polar, and you're going to administer that into a non-polar stationary phase, because C18 is a non-polar stationary phase. So this compound 2 will have stronger interaction to the C18 column compared to that of the compound 1, which is weaker in the hydrophobicity. So what happens? Number 2 will adhere to more time onto the column compared to that of the compound 1. So you can see compound 1 elute faster, and then compound 2. Since they vary in their hydrophobicity, you can see the difference in the retention time as they separate each other. And to understand the solvent polarity in terms of the separation, so let us take example of benzoate, the esters, but they vary in their substitution: methyl, ethyl, propyl, and butyl. 4 esters has been separated by using the polarity of solvents, water 20:80, where you can see separation is very, very poor because they are closely overlapping each other. And when you increase the polarity of water to 30 from 20, you can see there is a separation, but it is not acceptable because we have to look for the other system suitability parameters, measuring the resolution factor, the tailing and theoretical plates concerned to that. So it obviously fails in that matter. And when you still increase the polarity to 40%, you can see the phenomenal separation happens in the chromatogram. So the solvent polarity plays a very important role, and you can able to differentiate these esters. They slightly differ in the number of carbons as they progress one after the other, but the separation can be attained with the isocratic mode. And moving on to the choice of LC mode, suppose if your compounds are neutral or non-ionized, you can opt a reverse method. If your compounds are ionizable, you can opt ion pair chromatography. And if your compounds are normal phase, you can opt for isomers. If your compounds are inorganic ions, go for ion exchange. And if your compounds are high molecular weight like biomolecules, proteins, or carbohydrates, size exclusion chromatography is the right choice of LC method. And this pictogram depicts the types of elution. We have 2 types of elution in chromatography. One is isocratic, the other one is gradient. So in isocratic mode, you can see there is a constant flow of mobile phase ratio. That is, throughout the analysis, we maintain the constant ratio of mobile phase. Say, for example, you start the analysis with 70:30 of aqueous and organic phase. It should be maintained throughout the analysis the same. Whereas in gradient, you're going to change the polarity of the solvent from time to time. Say, for example, from 0 to 5, you fix 70:30, and from 5 to 10 minutes, it is 60:40, or later it is 50:50, like that. You're programming the ratio of the mobile phase so that you can separate many things in a mixture than a single component in a mixture. So that is how gradient employs, and mostly this technique is employed for impurity profiling, and we have a session for that by the other resource person, so it will be detailed over there. And these are the 2 different modes that are employed in the elution process of chromatography. So let us understand a little more here. So you can see in the first case, which is an isocratic mode, where the analyst has fixed the ratio of organic and mobile phase as 60:40, and you can see, of course, 6 components are separated, but don't you think it is a longer runtime? See, the analysis goes more than for 20 minutes or 30 minutes. You have to develop a rapid method such that the mixture of analytes can be separated in a shorter runtime. That is what really expected in a method. So the first thing, when it is been incorporated as isocratic, it's a long time analysis happened. And in the second case, you can see, of course, you reduce the runtime. You brought the analytes into a shorter runtime, but you see the separation that happens with the first 4 compounds are absolutely poor. So this is again the case of isocratic, just by varying the proportion from 6:4 to a 8:2. But now look at the gradient, where you are going to change the ratio of the mobile phase from time to time. Thereby, you can achieve a better separation as well as in a shorter runtime compared to that of the earlier cases. This is how the gradient helps in the elution process. So with this, I'm completing my part 1, which is on the knowledge component. Now I'm moving on to the second part, which is going to be most onto the components of HPLC, which can even describe the components starting from the mobile phase reservoir to the drain. Also, I will like to add few aspects onto the application in the later slides. So this is how the liquid chromatograph inbuilt system is available, and you can see the different components starting from reservoir, pump, injector, column, reductors, waste, and you have a signal processor recorder for data collection. So there are different systems available where you can work out on isocratic mode of elution, where there is one mobile phase reservoir and one pump which is controlled. Suppose you wanted to use 2 or more solvent, it should be pre-mixed before you introduce the solvents into the mobile phase. So this process is called as isocratic mode of addition, and system is available. This is a basic model of HPLC that is available. And the next one is high pressure gradient system, where you can see there is 3 reservoirs available, and each one is controlled by a pump, which is called a tertiary pump, which has been controlled separately for each mobile phase reservoir, and thereby the mixture of solvents is mixed with the help of a mixer in the system. And the rest of the parts are similar like isocratic, where you have an injector, column, reductor, and the signal processor. But this will create a high pressure if it is not properly mixed from the each pump. And the next one is low pressure gradient system, where you can see the presence of quaternary system of mobile phases are available, the 4 channels, with one pump controlled from the 4 channels. And for this, very important thing required is a degassing process. So online degassers are available in the system inbuilt. So degassing is very, very important, because when there is entrapment of any air bubbles in the flow channels or anywhere in the system will affect the the flow of the mobile phase, thereby the analysis cannot happen. So the degassing is very, very important internally as well as externally. So externally, the degas happens by using the sonicators to remove the air bubbles when you mix up the organic and mobile phase, as well as with the aqueous phase. The online degassers are inbuilt into the system, and also you have a setup called as purging into the system, where you can manually purge or automatically the purging can be done in a system. And this has to be done in practice every day in order to remove the flow channels blockage or any blockage in the column or in the entire system of the chromatograph. So this is most widely employed gradient system with a low pressure component. So apart from the other accessories, you can also see here in this particular pictogram, there is a degasser which is present for 2 individual reservoirs. And also you can see the presence of pre-column, which is nothing but a guard column, always employed before the main column in order to protect the life of the analytical column. And also you can understand the availability or presence of flow splitter, thereby you split the flow into the blank as well as the component that can reaches the reductors that is present. So these are the subcomponents which are present in the HPLC. And what are the criteria that you should look for analysis in HPLC? The very important component is a column, which is considered as an heart of the chromatograph. So because there it's the separation happens, and you should consider various criteria like the length of the column, because length of the column determines your efficiency of separation in terms of the number of theoretical plates that is being calculated in the column. So initially the column is new, that the number of theoretical plates will be more. And if the column is as becomes older in separating many analytes, the number of theoretical plates will go down. And the resolution also again matters with respect to the column length. And whatever the adsorbent that is packed onto the column has a serious impact onto the particle size, and the size should be minimal, experiences a wider surface area where the adsorption happens as well the separation later on. So these things should be considered as a criteria or critical parameters for choosing the solvent column in the practice. And also you can even look at the choice of mobile phase in terms of how much pressure it will develop when it is being introduced into the system. Mostly when you mix the organic and polar phase, there will be a formation of pressure, higher pressure into the system. So the optimum level of pressure that can be ideally withstand is 200 bars or 3000 psi. And the nominal flow rate that you can subject into the analysis is ranges from minute. And nowadays, the advanced techniques like UPLC or nano HPLC even utilizes less ml of flow into the system. But it should not, any flow rate should not be more than 3 ml per minute. Valve system where you can see the injection of a sample in terms of two position. One is load, the other one is inject. So in the load position, what happens is the port between the sample and the pump will be opened. You can see the opening, and you can inject the analytes that into the loading of the sample, right? You can load in any volume of sample, say for example 100 microliter or 200 microliter. But during the inject position, the port for pump and column will be opened, thereby only the required volume of the injection will be entering into the column. So in the load position, this port will be opened and pump to the column will be closed, and an originated, and thereby the analyte enters into the column. That is how the 6-port valve system works in a HPLC system. And when you look into the injectors availability, we have two types. One is manual injector, the other one is auto sampler. So manual injection can be done with the help of an Hamilton syringe, which is a fixed volume of syringe. It could be of 25 microliter or 50 or more than that. And it will be injected into this part of the injector, which is a manual injector, where it's called as rheodine injector. And using the syringe, or even sometimes using a normal syringe, the injection of analyte can happen. And there is a phenomenal auto sampler where you can load more than 100 samples of analyte at a stretch. You can program yourself, sequence yourself in the HPLC system. Thereby, this not require any analyst to just sit behind into the instrument, load the next day, provided you are properly sequenced the number of vials and the sample identity. So this is the output, and detector is brain of the chromatogram, where you can see how it is being represented. The x-axis is time, where your interest is to note the retention time, which is a qualitative parameter, and also the signal can be measured in terms of area of the peak or height. Mostly, practically, we go with the area of the peak because a symmetrical peak a Gaussian peak is expected in the chromatogram. So peak area is measured as one of the parameter, and retention time. These are the two important parameters that you can infer from a chromatogram, that is as an outcome from a chromatograph. And even you can look into the aspect of several types of columns that are available, like normal phase, reverse phase, size exclusion, and ion exchange. So as already I mentioned, the normal phase where the stationary phase is a polar, and you can see the presence of silica group in the particles that is packed into that. So most polar, least polar. On that base, the components will be separated. And in the reverse phase, you can see there is a extension of a carbon chain, which makes the polar stationary phase a non-polar, and thereby based on the polarity towards the non-polar characteristics, compounds will separate. And in case of size exclusion, gels are packed into the column where the molecules get separated based on the size of the analyte, right? So the small size of the analytes will entrap onto the gels that is packed, and the larger molecules which could not entrap will elute first. So here the separation happens based on the size of the molecule, whether it is larger or smaller. And coming to the ion exchange chromatography, here the column is packed with the resins. So you have n number of resins that are available, which can be classified based on strongly cationic, strongly anionic, weakly cationic, weakly anionic. And here the silica is embedded with anionic residues so that it can exchange with the cationic species. So more positive will be eluting than that later it is elute. So more positive will be adhered strongly to the stationary phase, so it later elute. And this elution can happen with that of the acidic mobile phase. And in case of anionic exchange resins, you can see the silica is embedded with that of the cationic residues, and thereby it separates the anionic species. So more negative species will be eluted later, and it can be eluted with the help of a alkali, like sodium hydroxide or potassium hydroxide can be used as a solvent. And apart from those packing materials which is packed in the column, you can differentiate the column in terms of the length and the particle size or diameter that is being packed. So you have a guard column to protect the main column. Fast column is nothing but column which is employed in UPLC, where you can get the retention time less than 2 minutes. And preparative column is a wider column where a larger amount of samples or analytes can be isolated, and then it can be estimated. And capillary column, again, they vary in the length and the diameter, and nano column even less than 0.1 millimeter is the diameter employed. And the much employed column which is routinely used in quality control is nothing but the analytical column. And coming to the detectors, there are many detectors available. The most widely employed is UV visible detector, PDA, or detectors are much employed. Apart from that, you have fluorescent detector, and see the level of limit of detection over there, femtogram level, which is more sensitive detector among the all. And also you have electrochemical refractive index detector is a universal detector. Suppose if your compound does not have a chromophore, it does not release an ions, it does not have any specific characteristic feature, you can go with the usage of RA detector, which even can measure the nanogram of samples. And the other detectors are listed. Now, how to choose the detector? As it is mentioned already, if you have a chromophores which has a real ability to absorb the UV or visible radiation, so such kind of compounds, UV visible or PDA detector is better. And fluorescent detectors can be employed for compounds which have a fused ring, heterocyclic systems, or highly conjugated systems can be employed for fluorescent detector. And conductivity detector for charged compounds or ions. Electrochemical detectors for compounds which can undergo oxidation or a reduction process where they generate the electrons. Their electrons can be captured and it can be estimated. And also we have refractive index and evaporative light scattering detectors, which can even not much employ this ALST, only for anything that do not have characteristic absorption in the other detector can be employed here. And coming to the application, you can see the HPLC can be much employed for non-volatile substances or analyte that is thermally unstable, because volatility and thermal stability is very, very important in terms of GC. So anything that does not require for a volatility or a stability, all those compounds can be estimated by HPLC. And you can see here the list of pharmaceuticals and proteins, biomolecules, heavy hydrocarbons. Even it can extend to the herbal medicines or cosmetics or plant extracts, or even to the nutraceuticals. So a number of applications are happening nowadays for the better separation by HPLC. So you can see here there is one animation video where you can visually see how the separation happens and the outcome is arrived. So this is how the separation happens. You can see the introduction of injector system here, and there the pink color compound that enters. You can watch the animation video. So once that pink color compounds enters into the column, you can see they separates into different bands, and once these bands reaches the detector, you can see the output of the chromatogram that comes in the signal processor. So there are 6 bands that are separated, and you can see the 6 compounds that are separated, and the response has been recorded here. So that's how the entire system works in terms of separation. So now looking into the parameters that is employed. So retention time is the one which helps you to identify the compound that is present in. So if any 2 compounds have a similar retention time, say for example here the compound A is around 5 minutes and compound B is around 15 minutes. So you can say compound A is different from that of compound B. If any 2 analytes have a same retention time eluting, then you can say there are same compounds. So retention time is a very important parameter which decides you to say whether the compound is present or absent. That becomes a qualitative analysis. And when moving on to the quantitative analysis, always concentrate towards the estimation point of view. So whether to determine compound in terms of its concentration or in terms of amount or to determine the percentage purity. So all these matters with respect to the defining the peak area of the corpse, how intense your peak, how high your peak is. So based on that, your concentration can be detected. If you have a more height, then the concentration is higher. If your area is more, the concentration is more. So peak area is a quantitative parameter which is being really interested to get from the chromatogram. So I just completed the component part now. I think can I have 15 more minutes to complete the session, madam?
Yes, ma'am. Yes, ma'am. Kindly proceed.
So you all agree to me that struggles are just tiny hurdles and it is not your destiny, right? So always for any analytical technique, problems will be encountered, and definitely as an analyst we all have a responsibility. Even the researchers who now works on HPLC system in terms of PG project or PhD or even a UG project should try to identify the problem and get solution for that. So that process is simply called as a troubleshooting, and I will not take much time in detailing. So I will be projecting the slides. One or few points I can discuss into this. So there are 5 main problems that are encountered when you analyze any analytes in the HPLC system or when you have HPLC system. So the one will be due to the pump, where mostly the abnormalities for the pressure happens, and the next one is leaks at the various stages of the system, and the problems with respect to the outcome, the chromatogram, the peaks are not good. They may have tailing, they may have more noise or drifts, improper shape of the or fronting kind of thing. So these are the other problems pertaining to the chromatogram. And there are also problems with respect to injection point, where you can see the leak, and also difficult to turn on the load position and inject position. And also there are other problems where you can smell, sight and sound. So quickly, I'll take up this session for next 5 to 10 minutes, understanding the pressure abnormalities. So where you can see there is no pressure reading as well as no flow. So immediately you should check for any entrapment of air in the pump, or sometimes if you are not filled properly the reservoir, mobile phase reservoir, then there happens this kind of problem. So that has to be checked and you should give the solution. So as I said, the purging before. So if purging is done, you can remove all the air inside the flow channels and also in the pump. No pressure reading, but flow is normal. Then you should check for the meters that are concerned with the pump. So there is a meter as well as there is a transducer that's which detects the signal or sends the signal and maintains the flow rate of the mobile phase. So these should be checked. And the pressure is steady, but you see that it's a higher pressure, because some systems may only ideally can allow pressure up to 200 bars or maximum to 400 bars or 3000 to 6000 psi. But if you see more than that, your analysis stops. So you can check for the column, any leak is there or improper column is being utilized, or the temperature of the column is very, very low. Either you can operate at an ambient temperature, or unless otherwise your method specifies that you should operate it at 30 or 35 or 40 degrees centigrade. So these can be checked when your pressure is high. And if your pressure is low but you have a steady flow, then you should see where there is a leak in the system, or sometimes the vice versa, the temperature of the column may be more. So you have to address these problems by giving the solution, or you can simply replace the any parts that are giving the malfunctions to the system. And next is pressure cycling, means the pressure will be internally circulating and not coming out. So in this case, you should degas the solvent and you can replace the pump seal, and you have to check the check valves. If it is not properly working, it can be replaced. So much of the work we cannot do, but you should definitely call a manufacturer or a service person to help you in this case. And leaky fittings, all the systems should be identified for any leak. So leak may be due to the loosened fits or the components that are fitted to that. So you can tighten them or replace them, or you can even clean them in order to avoid the leaks. And leaks at pumps are possible due to various reasons. So if there are leak, you can give the solution either by tightening them or you can give for a repair, or you have to go for a replacement of various valves that are present in the system. And injector leaks, as already I said, you should see the needle diameter, whether improper needle diameter is there, or needle when you look into the syringe of the Hamilton, it is not sharp, the end should be blunt, and if it is been dirt has been blocked over there. So all these things can be checked in order to give a solution to that. And column leaks, obviously the ferrule should be tightened, or you can rinse the ferrule, or you can reverse the column and work it out. So all these kinds you can do only if you experience in working out with HPLC on day-to-day basis. And detector leaks, of course, it is mainly due to the connection of detector to the waistline. If it is blocked, these leaks can happen on fittings in the detector, or even the failure of the gasket can lead to these leaks. And what are the problems you encounter with the chromatogram? You can see this is a normal chromatogram. Why do you say this is a normal? Because any peak that is a symmetrical peak. When you cut the peak into two equal half, it should give a similar area and height. Sometimes the peak will not be, normal. So this condition is called as tailing. So peak shapes and improper resolution also you can see. So this is a problem that is addressed. Now what you have to do, you should address this problem and give the solution. So the peak tailing may be due to blocked frit. So you have to replace the frit, or you can go for some other column. And column void is nothing but this is a space which is devoid of your packing space as well as the hardware. Hardware is nothing but the stainless steel. So that occupies some space in the column, as well as the packing material which is packed into the column will occupy some space. So apart from these two spaces, the empty space that is there in the column is called as column void. So that has to be filled. Otherwise, this all happens once you saturate the column for longer time. And also if you have used the wrong mobile phase, not properly adjusted the pH of the mobile phase, in that cases, the tailing can happen. And peak fronting means this is the condition of peak fronting. So your later part of the peak is symmetry, but the beginning of the peak is not normal. So in that case, you should reduce the concentration of the sample. This happens mostly because of the overlapping of samples. And peak splits can happen at the peak of split can happen at the peak where you can see due to the contaminants that is present in the column. So if you remove the God column and wash it or clean it, or you can even replace the main column, or you can wash the frits and other things, so that this kind of splits will not happen. And baseline drift is nothing but the noise that you can see here, the improper. So usually the normal line should be like this. You should create a baseline which is linear, and it should not be like this. So this is a problem encountered when you're not properly mixed your mobile phase, non-homogeneous mobile phase, or any air buildup in the column, or any impurities present in the mobile phase. All this leads to baseline drift. And baseline noise is nothing but the other problem, which is again a regular or it's an irregular one. The regular one you can see because of the leak or incomplete mixing, or there will be air in the entire part of the HPLC system, including the detector. So this creates, because detector is a one which is a sensitive component that responds to a chromatographic response. So if there is a block or kind of air entrapment in the detector, that leads to a baseline noise, but it is a regular. It even falls similar to that of the normal. It is called as regular. Now you see what is irregular. See, it is not linear to that of the normal, but it is somehow like this. So this is another problem which is mainly due to the air entrapment into the detector system. And sometimes if your long usage of lamp and the life of the lamp is going down, so this kind of problems will be arised. And broad peak is another one which may be due to most of the things whatever I've already addressed, like you are not prepared the mobile phase properly, or contaminated God column or contaminated main column, and you are maintaining the column temperature very low, broad peak can be obtained. And loss of resolution is mainly due to not fixing your method properly. You're not looking into the pH or pK of the method, or your mobile face is not properly adjusted to the ratio. So all these factors leads to the loss of resolution. And if your column is very very old and you are trying to develop some method into that, it can adhere only to maximum 1000 or 2000 injections. If you wanted to run more than that, definitely the number of theoretical plates will be low, and in the same pace resolution also will be affected. And injector problem, hard to turn, hard to load. Obviously you should adjust, or you should rebuild something, or you should replace the valve, or you should call for a manufacturer to solve that. Detected by sense, this may be kind of smell which address again the leak that is possible with the system. And sight is something where you can see through your eyes, maybe kind of warning lamps, or the meter readings are not displayed properly due to pressure abnormality, or lamp will not display properly the readings. So all these contributes towards the visualization, which falls under the term sight. So what is about the sound, the buzzers? Sometimes the location of the leaks that happens inside the system will be emphasized with respect to the buzzers, warning buzzers, and also the squeals are nothing but some irritable sound that comes out of a system because of the unfailure of the lubrication process into the system. So all these contributes the problems to the HPLC system. And as an analyst or as a researcher, we have comes to address these problems and solve it. And it does not come with one day or 1 week training. It can only come when you practice every day, starting from purging the instrument till addressing the problems. So the next parameter is about system suitability, which is very important. Those who are doing your PG project, UG project, or PhD thesis, or you wanted to publish a journal article, or you wanted to assure that your system perfectly working or to produce it. So retention time, resolution, theoretical plates, and asymmetry factor needs to be assessed. So retention time is nothing but the time that is taken for 50% of the component to reach the point of injection to the point of the detector. So that is nothing but the RT, R suffix T is nothing but retention times. So this needs to be addressed for every analyte. And resolution is nothing better the separation is happening. So this is a less resolution, and this is a better resolution or more resolved peak, because the separation distance is high. So this can be done with the help of a formula, 2 into retention time of the second peak minus retention time of the first peak divided by the sum of the width of the two peaks. Say for example, your retention time of the second peak is 6 minutes. So 6 minutes minus the first peak is 4 minutes, put 4, and divided by width at the baseline. You should calculate the width at the baseline, not somewhere here 5% or 10%. The base of width should be from the baseline. Okay. So say for example 1 centimeter or 1.1 like that. So if you calculate, that gives you the resolution factor for the separations. And column efficiency is nothing but that's again based upon the number of theoretical plates. What are theoretical plates? They are the imaginary plates which we cannot see how much it is there in the column that is packed, but you can calculate it based on the Gaussian expression, which is width is nothing but 4 times of the sigma. So when you substitute the number of theoretical plates in this formula, that is retention time by standard deviation the whole square, 4 square is nothing but the 16. That's how the 16 arrived in the formula. So we should know why these numbers are very important. Why 16 is in the formula? It's again, we should look back to the Gaussian peak, where the 4 sigma is the so Gaussian peak will be like this. It will be 0.5 sigma or 1 sigma, 2 sigma, 3 or 4. So exactly at 4 sigma you can exhibit a symmetry for a peak. So what is symmetry? Symmetry is nothing but when you divide or cut the peak into 2 equal half, it should give a similar area and the height. So that is how the formula arrived. And if you know the RT and the width, the peak width, you can calculate number of theoretical plates with this formula. And nowadays, if you incorporate the parameter into the system, it will calculate and give. But as a student, you should know the formulas to explore much onto the fundamentals. And asymmetry is nothing but predicting the symmetry of the peak. The peak should have a similar height and area, but here you can see it's a tailing. So asymmetry factor is nothing but predicting how much extent the tailing happened. So here the formula B by A. So the area, the width which is measured here in the later stage, divided by the width in the earlier stage. So B by A. Obviously, the width is more in the later stages, and you have to calculate the width not in the base, but you should calculate the width at 5% of or 10% of the height. So this is all. Once you practice calculating, you will be knowing better about this. So now we should have some limitations or specifications. Who has given this specification for us? USP guidelines. So USP guidelines says when you calculate the resolution factor should not be less than 2. So anything that is above 2 only, 2 and above 2 will be considered as a better separation. And number of theoretical plates should not be less than 2000. So when you purchase a new column, the number of theoretical plates will be 12,000 or 15,000. Even for if it is GC columns, gas chromatograph, it will be for 30,000. So if you see that your theoretical plates are less than 2000, and after you calculate or run the experiment, it's ideal to dispose the column, or you can recycle the column and then use it. And tailing factor should not be more than 1.5. So once if you achieve these system suitability parameters in your methodology, then you can go for a publication or submission of your book. And there are a few parameters you should learn about. I'm not going to discuss in detail, but any method, no, you cannot stop just by developing it. You should validate the method for its accuracy in terms of performing the recovery studies and precision by repeating many times. Repeatability and reproducibility matters here, and your statistical parameters are going to say whether it is precise or not. Specificity, how specific your analyte is going to react to your component in the method. And detection limit is about LOD, limit of detection, and quantification is LOD, and linearity, how your concentration is going to vary with that of the peak area, and range. So at what concentration range you are able to have accurate and precise method. And robustness is nothing but when you are deliberately changing any parameter. Say, for example, you are going to change the flow rate plus or minus this and that. You're going to change the detector wavelength plus or minus this. You're going to change the mobile phase ratio plus or minus. So whether your method is not affected by these changes. So that is what about the robustness of the method. So you can either follow ICH Q2 R1 guideline, or for bioanalytical US FDA guidelines gives you more input about this particular component. And when you want to set up a new HPLC facility for us or for a college just started, of course, you need a basic model of HPLC system. So Waters are the pioneers in this field. Apart from Waters Corporation, even the Agilent Corporation, and most of the academics make use of Shimadzu for many good reasons. Comparatively, it's of less cost, but highly efficient in separating. And apart from the basic HPLC system, you need to have this mobile phase filtration unit. This is a filtration unit, and along with that, a vacuum pump is required, and you need a sonicator for degassing the mobile phase. And apart from that, you should also have some calibrated apparatus. Not only the calibrated instrument like pH meter and electronic balance, you need to have a calibrated high standard glasswares and consumables, the grades of chemicals, reagents, and the water that you are going to use it in the HPLC analysis needs to be taken very much care onto that. And you need a SOP so that whoever operates the instrument perfectly or systematically operate it and maintain it properly. And of course, document is nothing but you should maintain a logbook for your usability of this instrument. And after installation, even you can start working onto it of all other subcomponents. And specifically for safety provision, you mode where you can prepare the mobile phases, because the acetonitrile mostly employed caustic solvents, and you can use some cabinets for storing separately these solvents. And you require some first aid kit or eye showers, or you can make use of goggles to protect your eyes and gloves for hands. So these are the minimum setup that you can explore when you want to set in a HPLC system. And tips for practical, specifically few points I would like to address, especially when you are using a buffer solution. Make sure that you have designed the pH for a buffer, and also the concentration of the buffer matters a lot in a separation. And when you wanted to adjust the pH, sometimes you see in a article, prepare buffer pH 7 and adjust the pH to 6.8. So you require something to adjust over there. So it may be an acid or it may be a base. So you always choose a acid or a base which has closer pKa to that of your but buffer of interest. For example, you wanted to prefer a buffer of 4.8, then in that case you should use acetic acid to adjust the buffer pH. So these things should be considered as a practical tip when you start working onto HPLC. And also you should take care when you're preparing the mobile phase where mixing happens, right? You're going to mix aqueous and the organic solvents. So when you mix aqueous and organic solvents, one may follow, say, for example, if the procedure says 9:1, so one may follow that he or she prepares 90 ml of the mobile phase organic and 10 ml of the or 900 and 100 for 1000 ml. So they mix, they measure separately these volumes and they mix it. That's one way of doing it, right? But when you take 90 ml or 900 ml and make up the volume to 100 ml, so definitely the chromatogram varies. So you can see in the first case, it is 90:1, where separately 90 ml is taken and 1 ml, that is 10 ml is taken separately and it has been mixed. That's the first case. In the second case, what the analyst has done, he has taken 90 ml and made up the volume to 100 ml by adding the remaining of the mobile phase. So that should not happen. So why it should not happen? If two persons doing a different procedure, obviously there is change in the chromatogram. And why you wanted to use acetonitrile, which is an expensive solvent in spite of availability of methanol with us? So for two reasons it is. So you can see the acetonitrile has very, very less absorbance compared to that of the methanol. Methanol has very higher absorbance compared to the acetonitrile. This is acetonitrile, the first one. The second one is methanol. So anything that gives a feeble absorbance, that should not have much contribution towards the analysis, that should be considered as a solvent. You all know that. So in that case, acetonitrile gives a very low absorbance compared to that of the methanol. On the other hand, when you look into the pressure that is exerted by the acetonitrile is absolutely low compared to that of methanol. Acetonitrile in 40 degree as well as acetonitrile, you can see at 25 degree the pressure is ultimately less, but the pressure is higher with respect to methanol when it is mixed with water. So these are the two good reasons for why we are mostly employing acetonitrile in the HPLC analysis, even though it is an expensive solvent. So pH adjustment, very important. You cannot just like that go and use your pH meter. It should be calibrated every day, because pH meter is a sensitive instrument which needs to be calibrated every day before you adjust for pH. So if the pH is 4, then plus or minus 0.05 is the limit. You cannot prepare 3.94 or 4.06 because pH has a serious impact on the pKa. So pH are employed in the column just to avoid the ionization of your analyte in the column. If you're not maintaining the pH by using the buffers, what will happen? The analytes will get ionized and you can estimate them as a whole molecule. So that for that reason, the pH is very sensitive to be addressed during your practicals. And grade of water, HPLC grade water should be used. The milli-Q is another important component that is required. You can buy if you are facilitated with good income. Otherwise, you can see water from the local market or from the local dealers, and you can see the pH of this water should be 5 to 6. And even you can measure the conductivity and assure that it is within 16 to 18 mega ohms centimeter. And of course, all solvents should have a low UV absorbance. An electronic balance again should be taken care. You should have a sensitive balance. You cannot use a physical balance or a mechanical balance for this. A sensitive electronic balance is required. And also please check for the calibration status of the electronic balance and what kind of container you can place inside the balance, because your sample may be solid or liquid. So accordingly, you should properly weigh the samples so that you can avoid the errors that happens with respect to weighing. So weighing part is very important. So see to that whatever the standards that you're using for a HPLC analysis of high purity substances. So if it is not pure, then your accuracy will be affected there. And how to weigh the hygroscopic property of samples, how you can avoid mistakes in doing the weighing process, and the preparation of samples is also very important. What concentration, how the dilution, how to calculate the concentration, and also you can say how the volumes can be adjusted perfectly, and whatever the apparatus you're going to use, or all calibrated apparatus or standard apparatus, and so on. And finally, the prepared solution, you need not to discard the solution unless otherwise it is required or mentioned in the procedure. You can even store the samples in a refrigerator or appropriately, and then you have to protect such samples from a serious impact on evaluation of the sample, because most of them are organic solvents. They are added to evaporation. So prevent it from evaporation, and also you protect it from light, or natural light, sunlight, or in the artificial room light if they are photosensitive. So these are the tips that you should adhere when you work onto the HPLC systems. And these are the formulas which already I touched upon in the slide, where the you can calculate LOD with the formula 3.3 into sigma by S. This is the slope, and it is nothing. It is sigma x minus x bar the whole square divided by n root. This is the standard deviation. Nowadays, you can easily get it. That should be maintained, and each and every component of an HPLC needs to be calibrated. If you take pump, flow of pump should be calibrated, and column O1, the temperature of the column should be calibrated with help of a calibrate thermometer, and pump flow and injection position, injection linearity. So many times if you inject the same volume, whether you're getting the same result or not. Suppose 6 times if you inject 20 microliter, your response is same or not. What is injector linearity? First time you're injecting 5, the second injection is 10 microliter, the third injection is 20, fourth is 30, like that. You're varying the injection volume, and similarly the response is varied or not. That is what you're going to look in terms of injector's linearity. So in injector precision, you're going to fix the same volume, but you're going to repeat it for many times. But injector linearity, you're going to vary the injection volume and observing the response, whether they're linearly increasing or not. And similarly, detector accuracy, you have to fix the specific wavelength and see to the response. And detector linearity, how your concentration responds to the peak area. So this is phenomenally the extensive procedures which needs a tabular column, which needs a proper calibrated thermometers as well as the glass flask to calibrate. Unless otherwise you calibrate and keep your calibration status, again the analysis is not complete. So these are the various advancements happening in HPLC. Just to have a look onto that. And so the hyphenated techniques, one of the resource person is today is going to talk onto that. So I'm just skipping that part. And software-driven HPLC tools are available to connect your HPLC method with that of the two important AI-driven approach, that is analytical quality by design as well as greenness. So you can use these kind of tools to explore your HPLC method is eco-friendly, as well as it is you have evaluated all the risks that is pertaining to the method by observing the various critical parameters with respect to the QBD process. And extraction is one of the important practical component which you should learn in detail. So I have added the many extended learning links in the reference part, so you can copy and just paste it in the Google. So many tips and different types of extraction techniques like solid phase extraction or liquid or protein precipitation, which is widely employed, especially when biosamples needs to be analyzed. So these are the extension or thing which I'm not detailing in this session. So these are the references and some of the videos, animation videos. And this PDF is more about what are the practical tips that you should follow during your HPLC analysis. And already I posted one Google form, so you can test your knowledge by addressing these questions in the Google form. So thank you. I'm happy to address any questions if you have. I think I completed on time.
Yeah, ma'am, but it's not fine. It's fine, ma'am. Really, we have got a good interaction with you, ma'am. As you said, there were two different parts of theoretical implementation part. Theoretical is a basic thing what we learn in the classes as students. Some of the students, the basic things what you know. Really, it's very nice exposure today for us, ma'am. Mainly with that animation, the video is very, very real. It's very nice. What we want to see nowadays, so many are being eager to know about the practical view of the instrumentation part, what's going inside the instrumentation part, the mechanism, what's going on. That has been explained by you. Really, it's very nice, very fantastic, ma'am. Really. And regarding the components and troubleshooting part is very, very nice, ma'am, because as troubleshoot plays a very important for new instrumentations, the problem what we face in each faculty in our colleges, what we face. Even kindly requesting you, ma'am, along with this, one day we'll arrange for hands-on training if possible. If possible.
Definitely, madam. Definitely,
Yeah,
we
yeah,
can do
yeah.
it.
Hands-on training with the instruments what we purchase because as we are in new colleges, our Manakula Vinayak college we purchased a new instrument of HPLC and with HUV spectroscopy with the year of second year itself. And it is a chance for us to make use of you peoples to have
What brand of HPLC you have, madam?
ma'am, it's Systonic what we purchased, ma'am, because there is no research work nowadays for us now for us at present. So simple Systonic we have purchased. And we are planning for the research oriented in a further fourth year, ma'am. That time we'll plan for a waters or as you said, the CMATs we will plan it. That is an issue, ma'am. Really, I am very
We have
happy.
covered the wider aspect of everything, but it will take more time to understand each and every component. Once if you
Yes.
experience the skill,
Yeah.
this is possible.
Yeah, that's the
Any
thing.
kind of help in future, definitely I'll be happy to do it, madam.
Yeah, definitely. It's a
Also,
pleasure for me.
I request the organizers to share the presentation slide to the all people who have registered.
Yeah, that's the thing. That's the
Because
thing. I am requesting the president, sir. Yeah.
something, because HPLC needs to be covered.
Yeah.
So that's how I've done. But even each component requires more to
More
learn.
time. Yes, ma'am. Yes, as HPLC is mainly concerned with the separation and identification, it is an infinity of time to isolate and separate for new drug, new method development and validation of protocols to be in. And really, we know very well about this, ma'am, as it takes more time. It's a small, like a mini webinars like this are organized by the president and secretary of APTA of Puducherry. Really, thanks a lot to interact like this kind of sections. What we have been, what our faculty has to be updated to all the current issues going on in our analytical techniques. Really, thank you, President Sir and Secretary Madam, for this opportunity.
Thank you so much, madam.
It's a good topic what we discussed today. And I have two questions with Madam.
Please.
Ma'am, as you said, Nano HPLC and UPLC, when only few colleges, institutions may have been purchased this HPLC, UPLC and Nano HPLC.
Yes, ma'am.
Yeah, if based on anything like seminars or anything organized for us, it be helpful for us to learn like a FDB program regarding that Nano HPLC and UPLC, ma'am. If time possible.
Definitely, madam. These are already in the Pharmacy Council of India PG syllabus.
Yes.
A theoretical component has been addressing in the academics. But as you said, practically it is very less available in the academic point of view. But there are industries who holds this UPLC and Nano HPLC. All that differs in the type of column and pump they use.
Yes.
We'll look into that, madam, and how best it can be helped.
Yeah. Thank you for your support, ma'am. We have got a good exposure with the recent what we have been experienced. Thanks a lot, ma'am.
Thank you. I thank the president and the entire team for this. And thank madam for this session. I'm so honored to share this session. Thank you.
Thank you, ma'am. Thank you. Mitosi ma'am and Dhanashree ma'am for your nice and wonderful session. And the elaborate session for our audience. And very thankful to you, ma'am. In future, we will definitely have a workshop. Thank you, ma'am.
Thank you. With your permission, can I lead the session?
Thank you, ma'am.
Yes, madam. Yes.
Thank you, sir. Thank you, ma'am.
Thank you so much. Thank you so much, madam.
Good morning. Now, I request all the participants to continue for the second session. delivered by Dr. C. and Nalini Madam, Professor from Principal, CL Medical College of Pharmacy, Thoraipakkam, Chennai. And the session is being chaired by Dr. Manikandan sir. He is the HOD, Department of Pharmacy and SRM College of Pharmacy, Puducherry, Chennai. I would like to give a small brief introduction about Manikandan sir.
Thank you, madam. Thank you for the introduction.
A brief introduction. Sir has guided 5 PhD students and he has guided 24 PhDs and he has guided more than 36 PhD students and he has published more than 51 international journal publications in international journals and more than 24 publications in nature journals and he has published 7 books and he has to his credit he has won the 2 patent grants and he has published 2 patents and one he has filed from that and he has received award from Dr. Puducherry Annual Award in the year of 2011 as a certificate of appreciation for an article title Stability Experience Method for Quantitative Estimation of MoneyDB Dihydrochloride API. And also he received gold medal for the best research paper in research in 2018, 17 and 16 during this Academy Institute of Science Technology. And he also received first prize cash award for guiding DG project in the year of 2014, coordinated by Tamil Nadu Pharmaceutical Welfare Session. He also received an appreciation of cash award for the journal publication in the year of 2011 and 11 to 12, 12 to 13 and 13 to 14 in Teachers' Day celebration organized by SRM Institute of Technology. And he's being acted as an external examiner for various universities and also acting as an examination paper setter and paper validation for various universities. But with this brief introduction, I request Manikandan sir to chair the session for Nalini Madam's session. Thank you, sir.
Thank you, madam. A greeting to all.
Thank you, sir.
I thank to the APTI Puducherry and the organizer of today's webinar to give the opportunity. I have the honor to introduce Dr. Nalini Madam, a renowned authority in the field of pharmaceutical science, as a today honored speaker, currently serving as a principal and head of the department pharmaceutical analysis, CL Medical College of Pharmacy. Nalini Madam has over 30 years of experience in the both academic and industry. She has taught at some same institution for a long time in variety of positions, including lecturer and assistant professor. Nalini Madam is an outstanding academic who graduated from the Tamil Nadu Dr. MGR Medical University with a Bachelor of Pharmacy and Master of Pharmacy, Pharmaceutical Chemistry, and the Doctor of Philosophy in Pharmacy. She also graduated from the Coimbatore Medical College with a Diploma in Pharmacy, with 98 published research papers, 64 of which are internationally indexed, and a considerable record guiding PhD student, postgraduate projects, and undergraduate research. Her research contributions are impressive. In addition to receive numerous honors, including the Best Teacher Award from Dr. Tamil Nadu, Dr. MGR Medical University in 2011. Nalini Madam has presented her research at 63 national and international scientific conference. In addition to her academic endeavor, Dr. Nalini Madam has actively participated in this member of esteemed committees and helped with curriculum designing, faculty development programs, and research guidelines at various universities, Annamalai, SRM University, and Mother Teresa University, among other institutions. Her leadership is planning multiple conference, workshop, and seminar, which has enhanced the academic community. Overall, is another way to her knowledge is demonstrated. Nalini Madam has 167 citation and amazing H index of 10, making her a true pioneer in the pharmaceutical science. Dr. Nalini Madam will presenting her thought on advancement in LC hypernated techniques. So please join me in welcome here. Thank you, madam. Now I hand over to the madam.
Thank you, sir. Such a nice introduction of me. Thank you so much, sir.
Thank you,
Shall
madam.
I start sharing the PPT?
Yes, ma'am.
Click பண்ணுமா? Is the PPT visible?
Yes, ma'am.
Mute. Yes, is the PPT visible?
Yes, madam. Yes, madam. That is
Okay, that's
Yes,
nice.
madam.
Okay. Yeah. So, good morning to everyone. It's a pleasure to welcome you all to this session on advancements in LC hyphenated techniques. So, as introduced by Dr. Manikandan, I'm Professor Dr. C.N. Nalini, Principal, CL Bade Mehta College of Pharmacy. Over the years, I have had the privilege of working closely with various hyphenated techniques, which are transforming the way we approach the complex analysis. Before we start, I would like to thank the APTI Puducherry for hosting the event. I thank Dr. V. Sri Janardhan, President, for giving me this opportunity to share the insights on this rapidly evolving topic. I also thank
Thank you.
Mr. P. Sanyappan, Vice President, Secretary Dr. Anita. I also thank the chairpersons and resource persons who have joined this event. My gratitude for the audience for being here. LC, as you all know, has been the backbone of the analytical science for decades. But the integration of LC with the techniques like MS, IR, and NMR has revolutionized its application across industries from pharmaceutical to environment and beyond. Today, we will explore how these hyphenated techniques are evolving by focusing on new generation hybrid instruments. By the end of this session, I hope you will have a clear understanding of where this field is headed and how it is it can impact all the research work. So now, first of all, we should know what is a hyphenated technique. Hyphenated technique is a combination or coupling of two analytical techniques, especially chromatographic and spectroscopic techniques. So here the chromatography works to separate the analytes in a complex mixture, and the identification is done with the spectroscopic technique, and both are connected with the use of a proper interface. These techniques have become more advantageous for analyzing the drugs and biomolecules, especially natural products, and to enhance capabilities. Example, LCMS, LCNMR, and LCFTIR. So now, before starting the session, the first LCMS interface was developed in late 1970s, but we can see that today's instruments are over 10,000 times more sensitive. This leap in technology is what we will be discussing today. We can see here in 1960s, LC coupling with MS was the challenge. First, LC was very popular during those time as a separation technique, but the researchers found challenges in coupling it with mass spectroscopy due to the incompatibility of the liquid, which flows with the high vacuum environment of the MS is maintained in high vacuum. So coupling LC with MS was a big problem. The key issue is LC operates in the liquid phase while MS is working in the gas phase. So we needed some innovative interfaces for the successful integration. In 1970s, the first breakthrough happened, and we came across the first LCMS interface. Like we had direct liquid introduction and moving belt interface, which we will be seeing the forthcoming slides. In 1980s, development of robust interfaces happened, like ESI and APCI came into existence. Then In 1990s, that is the era of hybrid instruments like QTOF and triple quadrupole taking the industry like a storm. In 2010, we can see to the present, modern advancements happened in the instrument technology, and we can see the Arbitrap technology, micro and nano LCMS came into existence, and of course, now we know we have AI and automation everywhere happening. Now, coming to the history, in a brief way, we'll explain it. In 1968, the first high voltage electron impact mass spectrophotometer was invented by Victor Talrose. The problem with this mass spectrophotometer was only a very small quantity of the liquid was able to be introduced into the mass spectrophotometer. Later on, there was an improvement in the technology, and we can see that in 1973, the direct liquid injection, liquid LCMS interface came into existence, and it was invented by Baldwin and McLafferty. In 1975, we can see the picture here. You can see the LC effluent inlet is happening here. You are able to see my cursor in the screen? You are able to see my cursor?
Yes, ma'am.
Yeah, you can see the LC effluent inlet is happening here, and we have the preheated gas inlet here, which is going to dissolvate the sample, and we have the corona electrode here, which is going to convert the sample into the ions, and the ions are entering into the MS here. So this is corona discharge interfaced mass spectrophotometer, which came in 1975. So later on, the instrument was further modified to introduce the dry sample directly into the mass spectrophotometer. In 1976, the moving belt interface came into existence. The LC effluent enters here, and as the belt is moving here over a heated coil, you can see that the solvent is completely evaporated and the ions are entering. You can see the coil here, heater is there, so the ions are entering into the ion source. This is in 1976. Then came the existence of thermospray interface, where thermal spray was used to convert the sample into the ionic form. So here, one important thing is this thermospray source design was able to handle the reversed phase solvent systems, and this was in complementary with the LC UV detection. So we can use the LC UV detection along with the LC UV MS. In 1978, the first APCI came into existence, and in 1984, particle beam interface was used, and in 1985, flowing fab came into existence. So now moving on to the different hyphenated techniques. So we have few examples I'm giving here. LCMS is there, GCMS, gas chromatography MS, LCNMR, LCIR, and CEMS, capillary electrophoresis coupled with mass spectrophotometer. Now, as we move on to the LCMS, this is the schematic diagram of LCMS. We can see that this is the solvent mobile phase is placed here, and these are all the solvent is a wire, and these are all the pumps through which the mobile phase will be pumped. And you can see this is the injection port, as explained by Dr. Vinodini in the previous session. You can see that this is the injection port through which the injection is given, and this is the column where the sample is entering with the mobile phase, and here we have the ionization source which acts as the LCMS interface, and the effluent from the column will enter into the mass spectrophotometer through the LCMS interface, that is the ionic source. And finally, of course, you have a data detection system, computers and softwares, everything is there. So now what is LCMS? So you have LC combined with MS here. LC is liquid chromatography. So it is, what is the use of LC? LC is a separation technique, whereas MS is an identification techniques. Mass spectrophotometer cannot separate the components. Only LC can separate the components. Mass spectrophotometer can identify the components. Better the HPLC method, better is the result. MS can separate ions, but not the physical separation of mixture of compounds. MS is one of the most sensitive and selective methods of molecular analysis. Very, very important, because it is being used nowadays in almost all the analytical procedures, and it gives you the exact molecular mass of the substance. Now you can see this. This is HPLC coupled with UV and mass spectrophotometry. You can see that UV, this is the HPLC. This is the UV or the PDA detector. Once the sample enters into the detector, and then the sample from the detector goes into the electron spray. Electron spray probe means it is the ionization source, and it enters into the mass spectrophotometry. So this is a coupled technique where LC is coupled with UV and MS. LC, UV, MS. So it's a now coming to the different modes which are being operated in LC-MS, MS, you have product ion scan, you have precursor ion scan, then you have neutral loss scan, then multiple reaction mode. These are all the different modes. Here the product ion scan. The product ion scan will detect only the product here. The precursor ion scan, in the precursor product ion scan identifies the fragments of the selected. You are going to select one product ion, and that product ion will be scanned here. Precursor ion scan detects all the ions that are producing a specific fragment. One specific fragment are being produced, that will be detected in the precursor ion scan. Then what is neutral loss scan? Identifies the ions losing a specific neutral molecule. Then comes the multiple reaction mode, most commonly used in all the industries, and this is highly specific for the targeted analysis, commonly used in quantitative studies. You have this common scan mode and the SIM mode also. In the common scan mode, it is qualitative analysis. It scans from the low molecular weight to high molecular weight, and it is going to scan the full mass spectrum, mainly used for quantitation and identification. When you go for the SIM mode, that is selected ion monitoring, as the name implies, you are going to select one ion and you are going to monitor it. That is going to be useful in quantitative analysis, measures selectively only the targeted ions. It is going to give you excellent sensitivity, selectivity, and repeatability. Now coming to the interfaces, that is various ionization techniques, what we use in LC-MS. The most commonly used are, you can see, So this graph is explaining what kind of compounds, for what kind of compounds you will use what kind of ionization technique. You can see for the very polar and high molecular weight compounds, this electron spray ionization can be used. That is ESI. Thermally unstable proteins and peptides and enzymes can also be detected using this detection techniques. See, we can see here the GCMS. GCMS is used for highly nonpolar compounds and low molecular weight compounds, whereas LC is useful for deals with high molecular weight and high polar compounds. And you can see there are different ionization techniques. Your APPI, APCI, and electron spray ionization covers almost all the high molecular weight and polar components here. For in-between components, you can use this APPI and APCA. In between polar and in between molecular weight intermediate molecular weight compounds. Now coming to the early stages of LC-MS development. So this is the picture given here. You can see this is the liquid chromatograph. In the liquid chromatograph, we had limited pumps and limited columns, not much variety. Nowadays, excellent variety of columns are available for every kind of separation. Here, the column effluent from the liquid chromatograph enters into the interface. That is the ionization source. Various ionization source available. We have seen already. This is the DLI EI, PBEI, particle. Then thermospray EI and dynamic fab. These are all the interfaces what we have seen in the history already. And then from these ions, from the ionization source, they enter into the mass analysis. Of course, mass analysis, we had single quad, triple quad, and 3D trap. Finally, we had a detector, but previously they all had low sensitive. Now, what is the problem or what is the challenge they faced when this LC-MS was developed? Problem is, we can see that the entire setup of the mass spectroscope or mass spectroscopy is kept under high vacuum. LC is operating with the liquid and you are going to introduce the liquid sample into the mass spectroscopy, which is being maintained under high vacuum here. So when I introduce a 1 ml sample with 1 ml flow rate, when it enters into the vacuum, the volume of the liquid is so much that the 1 ml becomes 27 liters or more, depending on what type of solvent we are using. If it is highly volatilizable solvent, more quantity of the liquid will there. So what happened is the pump was not able to take this volume, and the MS fails here. The mass spectroscopy fails here. So it is always advisable to maintain 1 ml or less flow rate in LCMS. Now coming to the latest LCMS, you can see improvement made here. If we see, the sample from the liquid chromatography enters into the ionization source. Here we have a variety of choice of pumps, choice of columns are available. Good literature is also available nowadays. We can do knowledge-based pressure ionization sources also. Mass analysis, there is tremendous improvement. We had now we have quadrupoles. Hybrids are available. Hybrids means 2 or more analyzers joined together. That is why we call them as hybrid instruments, and RB-Trap is the latest mass analyzer. And the sensitive, highly sensitive detectors are also now available. And one important thing what we have to notice here is the ionization source, where we are going to introduce the sample from the liquid chromatography into the ionization source, where we faced problem in the previous slide what we saw, that is overcome by keeping the ionization source outside the vacuum system. The ionization source has come out of the vacuum system, so you can make the ions here in the ionization source, and the ions can be introduced into the mass analysis. So these are all some of the commercially available LC-MS MS systems. You have Agilent QTOF LC-MS, where quadrupole is coupled with TOF, time of flight. That is, then Thermo Fisher Scientific Tribrid LC-MS. Then you have Shimadzu 5D Ultra E, Shimadzu 2D LC, Spinco Biotech Nexera FV. So you can see that this is the mass spectroscopy and this is your LC. So this is only the mass spectrum detector system. Okay. Coming to the components of the LCMS. So we know that LCMS is coupling of the LC with the MS. So this is your LC, which the parts of LC or the components of LC are already known to you. Now coming to the MS, we have the ionization unit first. Then we have the detectors. So this is the LCMS system with the interface. We have the UPLC or HPLC. You have an interface, something like ESI or APCI, and finally you have the mass spectroscope. So we are going to use aqueous or organic solvent with buffers in the HPLC or UPLC, and you will use non-volatile analyte molecules also. So when you put them into the interface, that is the ionization source, the ionization source is going to remove the solvent, it is going to ionize the analytes, and finally the ions will enter into the mass, which is maintained under high vacuum. Then it is going to analyze the ions which are entering into the mass analyzer. Finally, the ions will be detected by the ion detector. So now we will see the interfaces, that is the ionization sources one by one. So this is your ESI spray process, that is electron spray ionization. So this is the schematic diagram which explains the process here. So here you can see a bilayer needle. This needle is a bilayer needle, and it has got a very small opening in the tip here. The bilayer needle, through the inside of the needle, the LC effluent is coming. The sample from the LC is entering through the inside of the needle, and along the sides, the nebulizer gas is entering. Mostly it will be nitrogen. And when the liquid comes out through a small orifice here, we can say that is called as nebulization. We can see that the liquid sample is getting nebulized here and a spray is formed here. So once the spray is formed, here we can see the heated nitrogen drying gas is coming out through this opening. And this, as the heated nitrogen gas is coming into contact with these droplets, what happens is the desolvation effect occurs. What is the meaning of desolvation? The solvent is going to be removed here, so it becomes dry. And what happens is there is an voltage maintained between this opening and the needle here, plus or minus 5 kV, depending on the mode of operation, whether it is positive mode or negative mode. So there is a huge voltage difference being maintained between the needle and this openings, and because of this we can see that only the positive ions are being sucked into the ion mass spectroscopy. The positive ions are being sucked inside this mass spectroscopy. Actually, it looks like the picture what is shown here. This is the nozzle and this is the needle. You can see it has got two parts, and this is the liquid sheath which is coming inside through the needle, and this is the gas sheath which is coming outside the needle. Two openings, one is inside and the other one is outside, and this is the ion plume which is being heated to produce the ions. That's about your ESI spray process. So this is how exactly inside the mass spectrophotometer, this is how the needle looks like. Bilayer needle looks like this. This is one layer and the other one is this layer, and the needle will be placed at an angle like this. Never the needle is placed horizontally to this ion source, to this mass spectroscopy. Why? Because when you keep it horizontally at 180 degrees angle, the spray will directly enter into the mass spectroscopy. We want only the ions after drying, it should enter into the mass spectroscopy. So you can see that it is always placed in an angle. So this is the overview. The sample from the LC enters into the ESI. You can see it is the voltage difference is 5 kV between the entrance of the ions and this ion needle, and there is a drying gas which is going to dry the droplets. Finally, each and every ion are being separated and they enter into the MS here. So how does the ion formation happens? First step, as I told you already, it is desolvation. The solvent is being removed because of the heated gas which is being poured, which is entering into the ionization source. And the droplet fission, how does it? This is the bigger droplet, and as I dry it, the droplet is becoming smaller in size. Repulsion between the like charges, there is a bursting of this droplet happens, and more of small droplets are being formed here, which are again having like charges closer to each other. So more bursting. This happens again and again. This process is being repeated till we get the separated ions, which will be sucked into the mass spectroscopy. So this ESI can operate in positive mode is best suited for the basic drugs which can form the HCl salt. Like, what is a base? A base is a substance which can accept a proton. So it accepts the proton, it becomes M plus H plus. Abstraction of a proton from M. So this is best suited for the acidic drugs, and you get the formation of M minus H minus. The pros and cons, it is a soft ionization technique. The pros, if you see, it is a soft ionization technique. So not much fragments. It's a simple spectrum. Only molecular ions are produced. Multiply charged ions are also produced. So availing us, giving us the opportunity to analyze the proteins using this ESI. It's a versatile technique and most commonly used technique, and it gives you efficient ion production. Only problem with this ESI is it cannot ionize the nonpolar compounds. So next we are moving on to the APCI, atmospheric pressure chemical ionization process. The nozzle detail is given here. You can see again it's a needle. Through inside the needle you can see the liquid is coming. This is the inside the needle, liquid is coming. This is the nebulizing nitrogen gas which is coming from the outside of the needle. We can see this part is expanded here, and it is being heated by the coil here. So what happens is, as the sample comes out, it is getting dry. Desolvation portion is this, and it forms the ion plume, and the ion plasma is being heated by the corona needle here. Again, a voltage of 5 kV is being maintained here. So this is the principle behind APCI process. So this is the picture taken actually from inside the mass spectroscopy. We can see this is the APCI probe, heated APCI probe, and this is the needle, and this is where the ions are being sucked in. Then comes your APCI ionization. This APCI ionization is used for less polar compounds, but the mobile phase is more organic element we are going to use. So you can see the same setup here. From LC, the sample is entering here, and you can see the nebulizer gas also enters like this. This is the heater block which is going to heat the whole unit. And we see the solvent and the molecules coming out like this. So now what happens is the solvent, methanol, mostly methanol it will be used here, or if you can add methanol to the solvent system, if you are using more organic element, you can add methanol to that, and we can see that the methanol, the solvent, the S stands for the solvent here, the solvent abstracts the proton and it becomes HSH+. Then when there is a coronary discharge needle here, it is going to ionize it, the methanol or the solvent that is going to transfer the proton to the molecule here, and you get your MH+ here, which is going to enter into the mass spectroscopy here. So whenever we are using this APCI ionization along with the organic elements, we have to add methanol so that it can undergo protonation, and this will transfer the proton to the non-polar man. Then comes your APPI ionization. So this is same LC. You can see the sample from the LC, and this is the nebulizer gas, and this is the heater block, and here instead of the corona needle we are using a UV lamp here. So you can see that UV lamp is used to ionize the samples, and the ions will negative you can go for ESI, polar positive also you can go for ESI. Example of the drugs are also given here. For the non-polar you go for EI, and in between moderate polarity, positive and negative, you can use this APCI. So that is about the different ionization techniques which are used as the the quadrupole mass analyzer consists of 4 parallel conducting rods of hyperbolic cross section which are placed about the central axis, along which ions are being conducted. We can see this is the straight view of the 4 rods given here. The rods are connected to radio frequency RF and direct radius, and you can see that the adjacent rods are of opposite polarity. So for a given set of RF and DC potentials, ions only with the specific M by Z range will have stable trajectory. Means they will only reach the detector, and the other ions will be removed from the system, or they will hit the rods and they will be neutralized. If you are working in full scan mode, the RF amplitude and the DC voltage are scanned while maintaining a constant ratio. You are maintaining, but the RF amplitude and the DC voltage will be changed, and it will be in the range of increasing M by Z to reach the detector. But the drawback of the full scan mode is that ions of each M by Z will only spend a very short time in the analyzer. So only a very small amount of the ion will reach the detector per scan cycle. Going for SIM mode, selected ion monitoring mode, where the RF and the DC voltages for the specific ions of the interest only are applied. So only few ions will be detected and more number of ions will reach to the detector here. Then comes your time of flight detector. So you can see the animation here. There is a collision cascade which produces the ions, and these ions, they enter into the time of flight chamber here. This is the reflectron where the ions are hitting the reflectrons and they come back to reach the detector. Once the detector detects the ions, you can see the graph here. Or the signals are being and these ions, they enter into the time of flight chamber here. This is the reflectron where the ions are hitting the reflectrons and they come back to reach the detector. Once the detector detects the ions, you can see the graph here. Or the ions are being ions. Is there any problem?
No, madam.
Am I
No,
audible?
madam. Yes, ma'am.
Please,
Ma'am.
I'm getting an echo here. That's why I thought that maybe there is a problem.
Okay, no problem, ma'am.
So it's a mass analyzer that utilizes electric field to accelerate the electric field here. Electric field is utilized to generate ions, and these ions will be entering into the time of flight chamber here. So what happens here? You can see the lighter ions reach the detector first. The heavier ions take longer. So based on the weight of the ions, molecular mass, it is going to reach, the separation is happening here. Okay. So concept, if you see, the extractor gives all the ions with the ions which are produced here, they all have the same kinetic energy. When they travel into the field-free region, that is, there is no field here, TOS chamber, a reflectron is used here to increase the resolution. Longer the ions travel, distance is increased. There will be molecular weight. The time taken for the flight of the ions, it depends upon the molecular weight of the ions, and it is being detected by the TOF. Then ion trap cross section is here. These are the end cap electrodes. The ions are getting filled here. And the mass analysis and the fragmentation both occurs in the same space only. There is a limit for the number of ions that can be trapped inside the ion trap, because the Coulomb charge in this limit is exceeded, and there is a decrease in the mass accuracy, and there is a resolution happening here. Again, this can happen in two modes. One is scan mode, and the other one is MS mode. There is a limit for the number of ions that can be trapped inside the ion trap. Next is the RB trap. This is the latest development. RB trap is an ion trap mass. Again, you can see it consists of this is the outer electrode, outer barrel-like electrode, and a coaxial inner spindle-like electrode. This is where the ions are going to be trapped, and they will be in an orbital motion around the spindle. When they are spinning around this spindle-like electrode, there will be an image current generated from the trapped ions by the generated, and it will be detected by the outermost electrode, and we are going to Fourier transform the signals what we are getting from this RB trap, and that will be appearing as a frequency signal which is going to get converted into a mass. This is the actual picture of the RB trap analyzer. So now coming to LC-MS-MS, this is how the graph looks like. So this is the LC component where all the components are separated. So when all the components are separated like this, if we click on to one particular peak here, we will get the mass spectrum of the peak here. We can see here the mobile phase used is water with 0.1% formic acid, ACN with 0.1% formic acid, gradient elution, and ESI in the positive mode it has worked. So this is the advantage. All the scans, all the peaks can be scanned through mass spectroscopy in a single run. You can see the separation took only 2 minutes separation. Now coming to the quadrupole, this is the hybrid instrument. What do we mean by hybrid instrument? It is the LC-MS. In the MS, again, we are going to connect two analyzers here. We can see not two, triple also is available nowadays. You can see this is the LC. The quadrupole time of flight LC-MS. This is launched by Agilent Technologies. So what is the main feature here? Superior ionization technology that is going to give you high sensitivity. There are two mass analyzers being used here. You have the quadrupole ions based on the M/Z ratio, and time of flight is going to measure the ions flight time across the TOF chamber. Okay, so you can see the sample which is coming out from the LC system is passed through the stabilizer, and it is going to produce fine droplets, and it enters into the MS system. Then from the MS system, it enters into the hexapole ion guide. Hexapole ion guide means here. This is the hexapole. 6 poles are being used. Quadrupole means 4 rods will be used. Hexapole is 6 rods will be used. The lens is present in increase the ion transmission, and it is going to will be entering into the collision cell. This is the collision cell here. What is the role of collision cell here? The precursor ion which is generated in the product ions and the neutral fragments, they will form a beam of ions for better sensitivity, and it is going to improve the mass accuracy. The collision cell, see in this quadrupole, you have selected mass filter. You have selected one ion. That ion will enter into the collision cell where it will be collided with the argon gas which is present there, and it is going to form fragments. And these fragments, then they will enter into the TOF analyzer where they will be analyzed and separated. And finally, they reach the plate detector. This is the working of time of flight LC-MS. Q time of flight LC-MS. Advantages, if we see, it has got high sensitivity, higher mass accuracy, ultra high resolving power because it is a hybrid instrument, fast data acquisition rates, and you can switch the polarity rapidly. Applications, it has got numerous applications: toxicological analysis, food analysis, environmental analysis, pesticide identification, characterization and quantification of biomolecules, confirmation and identification of proteins, and therapeutic drug safety. Now, this is a tribrid MS. Why? Because we are having here, it is a fusion LC-MS system which combines 3 mass analyzers. You have the quadrupole, you have the RB trap, and linear ion trap mass analysis. Okay, it is mainly used for the analysis of complex analytical sample, injection, then excitation, and finally detection. It's a particle trap mass analyzer which comprises of 2 external electrodes here and a focal terminal which empower them to go about both analyzer and detectors. It can act both, and that's about the B-trap fusion LC-MS. So it consists of an ion source, lens, active beam guide. These are all the normal instrumentation parts, components. Particles entering into the RP trap are caught through electrodynamic crushing. That is, RB trap we have seen already, it rotates. The spindle-like electrode rotates. So there is a focal anode and it is going to rotate around it. Various particles will waver at various frequencies. So the swaying frequencies will be detected by the external electrode. And you have a quadrupole also here, which has got 4 parallel metal rods, and this we have seen already. It is connected to pair, each opposing rod pair is connected to RF and DC offset. The ions travel down the quadrupole between the rods based on their specific M by Z ratio. So the linear ion trap analyzer will store the ions in a fixed linear trajectory so that they can be used again after some time. Now coming to the advantages, increase trapping ion, higher resolution we get with this. It removes all the interferences, excellent selectivity and sensitivity because we are using 3 analyzers parallelly here. Even we get detailed structure of small molecules, high accuracy and precision applications. It is used in glycoproteomics analysis, determination of peptide fragmentation patterns, ultra-trace analysis, multi-elemental analysis, protein analysis, and drug metabolite identification. Now coming to the 5D Ultra E, it was launched in 2013 by Shimadzu company. It has got combination of 2-dimensional GC. It is a GC-MS, HPLC system. GC is also there, HPLC is also there, and a triple quadrupole mass spectrophotometer is there. All are connected in a series here. So what is the work of HPLC here? HPLC allows the separation of the analyte from any complex matrices. and they can be specifically set up for targeted analysis. The eluent or the effluent from the LC is injected into the GC system, and this contains only the target compounds. Target components are selected by the LC, it enters into the GC. So GC, it works under higher temperature, so it will remove all the solvent residues. Then the eluted components are inserted into the GC system. The two-dimensional GC system separate the components more efficiently than the one-dimensional GC system. They are then sent into the highly efficient MS, which is a triple quadruple system that is going to analyze the analytes by their mass to charge ratio, and it is going to give you an accurate reading. The 5D integrated software is used in this instrument. Sensitivity, specific analysis, even with trace concentrations, large volumes of samples can be injected. Easy to use software is available. Powerful analysis of trace components eliminates the need for liquid nitrogen here. High accuracy and precision. Okay, applications mainly in coal tar and sulfur compounds determination. Then we move on to 2D LC. It is a comprehensive two-dimensional liquid chromatography. So you can see that we have both quaternary pump and isocratic pump. In the picture it is shown here, and you have the normal phase liquid chromatography column here, and this is the RPLC column. That is why it is two-dimensional and sulfur compounds determination. Then we move on to both type of columns are being used here. Okay, the principle behind 2D LC is two distinctive chromatographic columns. One is NPLC column, normal phase chromatographic column, and the other one is RPLC. They are associated in succession, and so whatever is separated in this column will enter into this column, and it will get separated again. Okay, two-dimensional liquid chromatography system consists of the same HPLC system only. You have pumps, autosampler, detector, and columns. The sample is injected into the system using the autosampler. Then it is passed into the separating column and detected, and the whole process is again repeated. That is, the effluent from the first column is pumped on to the second column, and it is being detectors. The detectors used here are UV detectors. MS also can be used. You can use fluorescence detector, RI detector. Two-dimensional chromatograph will be produced here, but the disadvantage is extremely long time scale. Even from few hours to several hours it will take. Advantages, if we see, high resolving power, increase in peak capacity, and there is overlapping of peaks in the first dimension. Closely related compounds can be separated. Separated mixtures that one-dimensional LC cannot separate effectively. Then coming to the applications, it is used in chiral analysis, trace analysis, impurity profiling, herbal medicine, bioanalysis, and food testing. Now we are moving on to triple quad configuration, where 3 quadrupoles are connected in quadrupole analysis. Analyzers are connected in succession here. Here, if you see, this Q0 is a filter. There is no field being applied here. The ions are entering directly into 0. They go into the Q1 region here. So when they go into the Q1 region, you get your M plus ion. And this M plus ion, it is the Q1 is doing the scanning. So the only Q1 is going to give you the M plus ion. Collision with the argon gas or the helium gas. Fragment ions are produced and they are going to enter into the Q3. This is your collision cell where collision is taking place. From Q1, the molecular ion will enter into the Q2, which is a collision cell. Here, the argon gas or the helium gas that is going to produce collision, fragment ions will be produced, and these fragment ions will enter into the Q3. The Q3 is a scanner, so it is going to scan the entire M by Z ratio of the fragment ions, and the mass spectrum will be produced. Now, if you see here, you can see that Q1 and Q3 are the standard mass filters. They can scan the mass sequentially, and this can be used to select a single mass. Q2 is a gas-filled chamber which acts as the collision cell where actually the fragmentation occurs. Q2 is not a filter. It is going to accept all the ions which is sent by the Q1. Q1 is the filter which is going to select the ion and it is going to put it into the Q2. Okay. Now, if you see the advantages, if you are not able to do a good sample preparation, even the dirty samples can be analyzed using this triple quad configuration. That is the major use of this. Metabolite studies are also, this triple quad configuration plays an important role. So now coming to the advantages of liquid chromatography and MS, if we see, it is useful for labile analysis. Thermolabile analytes can be analyzed, polar compounds analyzed without derivatization, high molecular weight compounds analysis, and it does not involve a lengthy cleanup. That is the advantage of LC. When it is coupled with the MS, we can see additional structural elucidation is possible. There is further reduction in cleanup. It is mass specific, and there are various useful MS modes also available. To coupling of LC with IR, next hyphenated technique, LC-IR. Here, this is the instrumentation part, LC-IR. You can see that the effluent from the column enters into the interface, then it enters into FDIR. So there are two kinds of interfaces for solvent approach. You have the drift approach, buffer memory strategy, application, and identification. It is mainly, you know that IR is mainly used for the identification of functional groups and organic compounds. Okay. So one is flow cell, two types based on solvent approach is very much common. The effluent from the column will flow into the sample cell and the detection is done in the line sequence itself. There is interference from the mobile phase here. Then the second method of interface is the solvent elimination approach. This is the preferred mode. We can see here, this is the solvent removal interface. You can see we are using a disc here. Here, as the solvent is coming out from the column, we are going to use KBr and KCl here. So the solvent it is going to take the sample from the column. Solvent will be evaporated. Sample approach is very much common. The effluent from the column will flow into the sample cell, and the detection is done in the line sequence itself. That is interference from the mobile phase here. Then the second method of the solvent will be evaporated here. The sample along with the KBr and the KCl will be entering into the FTIR. As the solvent is coming out from the column, we are going to use KBr and KCl here. So the solvent LC-NMR. This is the diagrammatic representation of LC-NMR. This is the LC part. Though this is the HPLC injector, and this is the column. The column outlet enters the LC-NMR interface. This is the LC-NMR interface, which has got multiple loops here. You can see here. They are called as storage loops, where the ions are stored for further usage. And they enter into this is the flow cell, inline flow cell. So the sample flows into the flow cell and it will be detected by the detector. That is the LC-NMR system. This is the LC part of it, HPLC, which is connected with the NMR with the interface here, the LC-NMR interface. It is used for the simultaneous separation and identification of NMR active compounds which are present in the mixtures, complex mixtures or all types. Only compounds which are active in NMR can be detected using this LC-NMR. It is available since it started in the year 1970s, and the first paper was reported in 1978. Okay. So the LC-NMR works in two modes. One is continuous mode and the other one is top flow mode. Okay. And you can use the UV visible detector also can be used as a primary detector in this detector. From the UV detector, the flow is guided on to the LC-NMR interface, what we have seen in the picture, and it is equipped with additional loops for the intermediate storage of the selected LC peaks. The flow from the LC-NMR interface is then guided either to the flow cell. This also we have seen in the picture, NMR probe head, or to the waste receptacle. In most of the LC-NMR operations, RP columns are being used employing a binary or a tertiary solvent mixture with isocratic or gradient elution. The solvents used are deuterated solvents. So we can see ACN, using eluents that have few, or you have to use deuterated solvents, or you can use solvents which are having few H1 NMR resonances. Okay, at least one deuterated solvent should be used. And another availability, the valve switching interface is a versatile alternative for this interface. Coming to the applications of LC-NMR, identification of drug degradation products, low level isolated and identified. This technique is used for tracking pesticides, herbicides, organic pollutants, and environmental monitoring, electrophoretic mobilities and structural information, structural elucidation of natural products, mainly for natural products, complex mixtures of all and bioids can using this LC-NMR. Now next is HPLC ICP-MS. ICP stands for inductively coupled plasma. So this is your HPLC part of it. So here you can see it is ICP torch. The ash will enter into the mass spectroscopy here. This is again one more hyphenated technique. HPLC here is used for separation purposes, while ICP-MS is useful for non-volatile compounds. Mobile phase composition can be isocratic or gradient. Then the sample from the column, it enters into the ICP-MS detection system, and it is connected to the MS system with an interface. ICP-MS is mainly used for the detection of metals, inorganic, organic. Then comes Nexera FV. It is by the Spinco Biotech company. This PAT analysis, that is process analytical technology, it plays a crucial role in controlling the quality of products. It's all the steps, like we are going to do the sampling in all various stages of manufacturing, and every stage it has to be analyzed. So for that, this Nexera FV is very useful. Online flow analysis technology. LC system that automates the process of reaction and test solution dispensing. Through a flow-through vial, the sample will be collected using the auto sampler. You can do the synthesis evaluation also. It is applicable for both flow, and it can also be used for dissolution testing. We can see here. So this is the online analysis of flow synthesis. This is the flow synthesis, the column. This is the flow through vial. This is actually the instrument, Nexera FV system. It consists of the flow through vial here, and this is the column. And this is the out, in and out in the column. Okay. Online LC system that automates the process of reaction and test solution dispensing. So it can take the sample directly using the auto sample, and you can do the online analysis here. This is monitoring. That's going on in between also we can monitor using this Nexera FV system. And this is dissolution testing. So in between the process, manufacturing process, we can do the dissolution testing also using this Nexera FV system. Definited techniques are useful for dissolving difficult analytical problems. Complex samples can be analyzed and separated and identified using hyphenated techniques. It requires less time for research. Automation is possible. Increasing flow of samples. Improved repeatability. Since it is a closed device, pollution is also reduced. Improved selectivity and excellent separation efficiency for complex mixtures. So coming to the various fields like forensics, environmental, food industry, and other textile industries, pharmaceuticals, and biopharmaceuticals. In forensics, it is used for the analysis of drugs of abuse, blood and urine analysis. In environmental, water, soil analysis, and ant analysis. In food analysis, it can be used for pesticide residues testing, food additives and sweeteners testing, and veterinary drugs. In biopharmaceuticals also, antibody drugs and protein and glycan analysis can be done. And you have the pharmaceuticals. We know that phospholipid profiling, chiral drug analysis, and bioanalysis, everything can be done using this LCMS series. Then you have the industrial applications like textile testing and discharge. So, on concluding, this LCMS has transformed analytical sciences. It gives unmatched groundbreaking discoveries in pharmaceuticals and environmental analysis. As technology continues to evolve, LCMS remains at the forefront of analytical advancements, empowering researchers to unravel complex challenges with efficiency and accuracy. By embracing these innovations, we move closer to realizing new opportunities in science and industry, ultimately enhancing the quality of life worldwide. So, with this, I conclude this presentation. Thank you all for your attention. Thank you.
Thank you, madam.
Thank you, sir.
Thank you, madam, for the insightful and enlightening section on advancement in LC hybrid technique. Your expertise and deep knowledge of subject have truly expanded our understanding of the critical area in pharmaceutical analysis. The advancement you shared today in liquid chromatography CI extra are incredibly valuable, particularly for those as working and field of pharmaceutical analysis, drug development, quality control. We also deeply appreciate the way you highlighted the importance of sensitivity, resolution, and selectivity in hybrid techniques, as well as the potential for the quantitative and qualitative analysis in complex materials. It is clear that those developments are shaping the future of pharmaceutical research and clinical applications. On behalf of everyone here today, I would like to extend our sincere thanks to Dr. Nalini Madam for taking the time to share her knowledge with us. We are grateful for the opportunity to learn from that distinguished expert in the field. We also thank our audience for your active participation and attention. We hope you are leaving today's section with valuable insight that influence your work moving forward.
Thank you, sir.
Thank you, madam. I have some doubt, ma'am. That 2D chromatography, which type of sample we are analyzing, ma'am? Hello? Thank you, madam.
Yes, sir. Polar samples can be analyzed. More polar samples and complex mixtures which cannot be analyzed by a single something like our 2D TLC, where we do complex mixtures, we separate. Like that, we can use this 2D LC also.
Okay, ma'am. Thank you, ma'am.
Yes, sir. Yes, sir.
Yes, I have a hand over to that. The organizer, Anita, madam.
Thank you. I take this opportunity to thank everyone and especially the organizers, APTI branch of Puducherry. Thank you so much for giving me this opportunity to present this topic. Thank you all. Thank you.
Thank you, madam.
Secretary, madam.
Yes, ma'am.
Anita, ma'am. Yeah.
Is it audible, sir? Hello?
Yes, yes, ma'am.
Thank you very much, madam, for the elaborate session. I thank you very much on behalf of APTI Puducherry State Branch. And I hope we will be doing the further sessions in these connections in future. Thank you, ma'am. Thank you for your support. And thank you, sir, Manikandan sir, for your valuable time spent. Thank you.
Thank you.
Thank you, madam.
Thank you. Thank you, ma'am. Thank you. Thank you.
Thank you, madam. Thank you, madam.
Ma'am, actually, hyphenated technique is a very big topic. In fact, the triple quadruple itself, it needs nearly half an hour time. I just tried to condense everything in the time given to me. Maybe we will have an elaborate session later on, including the interpretation
Definitely,
part of
ma'am.
the
Definitely,
website.
ma'am.
Thank you, ma'am.
Definitely,
Thank you
madam.
so much.
So
Thank you,
much,
ma'am.
madam. Thank you.
Thank you,
ma'am.
ma'am. Thank you.
And dear participants and respected dignitaries, I request everyone to have a lunch break, and we will restart the session by 12:50 p.m. Stop 12:50 p.m. to 1 p.m. We will be having our introduction sessions, and sharp 1 p.m. the session will be starting. Please kindly join on time. Thank you. Thank you. Thank you for joining the session, everyone. Thank you.
Thank you all. Thank you.
Thank you, madam. Good afternoon. Good afternoon, sir. Is it audible? Hello.
Yes, madam. It is audible.
Thank you, sir. Good afternoon to one and all. I welcome back the all participants and the dignitaries to the afternoon session. And the session, the current session is given by Dr. N. Krishnaveni, Madam, M.Pharm PhD, Professor and HOD, Department of Pharmaceutical Analysis, JSS College of Pharmacy, JSS AHER, OT. And the topic is ensuring drug safety, the role of impurity profiling in pharmaceuticals. And the session is going to be chaired by Dr. R. Karthikeyan, M.Pharm PhD, Professor, SBVU. Professor R. Karthikeyan, sir, have been obsessive about finding novel drug molecules from terrestrial and coastal plants that have potential antimicrobial and anti-inflammatory and anti-cancer activities. His research has focused on isolation, identification, structural elucidation of bioactive molecules and evaluation of pharmacological activity by in vitro and in vivo models. Sir has obtained his bachelor's degree in 2001 in pharmaceutical sciences from Tamil Nadu Dr. MGR Medical University, Chennai, Tamil Nadu. He obtained his master's degree in 2007 in pharmacology from the same university. He completed his doctoral degree in 2018 in the area of pharmaceutical biotechnology from Acharya Nagarjuna University, Andhra Pradesh, India. He received many awards and certificates during M.Pharm and PhD studies for his research contribution. He has 17 years of teaching experience and research experience. He has published more than 131 papers, including national and international reputed journals. And he has presented more than 20 papers in national and 2 international conferences. He was awarded with 1 research Australian patent in his credit, and he published 6 research monographs and 5 book chapters with International Publishing House. He received Best Research Feature Award consecutively during the year of 2014 and 2015 from Vignan Pharmacy College, Guntur, Andhra Pradesh. He received totally 29.5 lakhs rupees as research grant from AICTE, MOFPI, SERB, for various natural product researchers as principal and co-principal investigator. He has 4 years of pharmaceutical industry experience from TTK Limited and Novel Drugs Limited. He is having more than 16 years of teaching experience and also in research. Presently, he is working as a professor in pharmacy at School of Pharmacy, Sri Balaji Vidyapeeth, Deemd University, Puducherry. And he is nominated as a treasurer in our Puducherry State. With this brief introduction, I request Professor R. Karthikeyan, sir, to chair the session. Welcome, sir.
Thank you, madam, Anita madam. Thank you for your elaborative introduction about me. And today's, afternoon session by Dr. Krishnaveni Nagappan. She is a professor and head of the Department of Pharmaceutical Analysis at the Jesus College of Pharmacy, Ooty. With 20 years of experience, she has published over 90 research papers and 3 book chapters. Her research interests include impurity profiling of drugs and pharmaceuticals, stress degradation studies, characterization of degradation product, and nutrikinetic assessment of functional foods. She has guided 60 postgraduate students, 7 doctoral candidates, and 5 doctoral candidates in stress degradation studies and food analysis. She has received grants to attend and organize conferences and seminars and has been a mentor for several projects. Then she has also organized workshops and conferences in the field of pharmaceutical analysis especially. And more than 1 crore of sum of rupees was received by her for her research projects alone from DST FIST, DST WOS scheme, and in case of ICMR. With these meritorious achievements by Professor Krishnaveni Nagappan, I welcome her to give her speech in impurity profiling. Over to Krishnaveni Nagappan, madam.
Yeah, thank you, sir. So thank you for the brief introduction, sir. Thank you, and a very good afternoon to one and all who have joined this online conference. I personally take this opportunity to thank the President, APTI Puducherry branch, Dr. Janardhanan sir, for the initiative. Because when we had a conversation with him, he said that this was the first conference being organized by him after he had taken as the APTI President of the Puducherry state. And I'm also happy that all the speakers today are all who are specifically working in the field of pharmaceutical analysis. So today my presentation I'm here to give some insight into how impurity profiling studies are being carried out and what is their role, what are the various impurities which could be seen in when we are going for a pharmaceutical industry. So I'm sharing the entire screen. Is my presentation visible?
Yes, madam.
Yes, sir. In slideshow mode, am I audible?
Yeah, you're audible, madam.
Yes, sir. So are my slides moving, sir, up and down?
No, madam. Now it is moving.
Yeah, this is the second slide. Is that fine, sir? Third one?
Yes, madam. Yes, madam.
Yeah. So impurity profiling, especially in pharmaceutical analysis or in the pharmaceutical industry, is one of the major area of research which has gained a lot of importance nowadays because recently few of the products which were containing the nitrosamine impurities were withdrawn from the market. Well, once they have entered, even for very old drugs like ranitidine and all, the drug has been withdrawn from the market in various parts of the world because of the presence of these nitrosamine impurities. So whenever we are talking about a pharmaceutical industries, the basic objective of a pharmaceutical industry is to provide a good quality, a safe as well as an efficacious drug product to the patient, and that should also be in the affordable cost. So the safety issues are basically determined through the pharmacological and the toxicological profiling, which is performed well before the drug enters into the market. And once the drug enters into the market, based on the storage conditions or based on the impact on the genotype of the individual persons, there are certain changes which are also being monitored. So any impurity which is present in a pharmaceutical compound can not only be an organic material which is present in your drug compound, but apart from that, it can also be a residual solvent which is used for preparation of the active pharmaceutical ingredient which remains in the API, or it could be a catalyst which was used during the manufacturing, or it can be a drug and what we call the excipient interaction can also take place, which can lead to the formation of an impurity. So they are addressed from two perspectives as per the International Council for Harmonization guidelines. Chemical aspects, these impurities has to be classified and identified, and the list of impurities along with their specifications, that is how much of each impurity is present in the product which is being manufactured, along with the analytical technique which is used for quantifying those impurities has to be provided, and the safety aspects of the impurity should also be established. That is, we have to qualify the impurities, means the quantity, what is the maximum permissible limit, we call it as. We have to quantify how much is permissible per dose of a particular active pharmaceutical ingredient, and if it is present in a much lower level, then what is the safety as well as the toxicity effects of those impurities. So all these things has to be characterized before an API or a drug product enters into the market. So the chemistry aspect should also be cleared, as well as the safety aspect should also be cleared. So any impurity which is present in an API may be formed from the following three. It can be any one of the three. So one is the organic impurities. As per the ICH guidelines, the impurities are classified into three. One is organic. It can be a process or a drug-related impurity, or it can be an inorganic impurity, or it could be a residual solvent, as told earlier. And even if they are present in very, very small quantity, they may have an influence on the efficacy, because the assay percentage will decrease as the percentage of the impurity increases, and it also matters for the safety of the patients who are consuming it. So there exists a common term which we call it as the impurity profiling. What are the different types of impurities which is present in the manufactured API or in the developed a drug formulation? And this impurity profiling includes two terms. One, we call it as the identified impurities, and the other we call it as the unidentified impurities. What is meant by an identified impurity? If it is beyond the threshold limit as specified by the ICH guidelines, the structure of that particular impurity has to be identified, and the safety aspect of those impurities has to be established. What is meant by an unidentified impurity? If a particular impurity is present in less than the threshold limit, than the specified limit, the structure need not be identified. They all together can be considered as unidentified impurities. So how do we set this threshold limit? So for setting these threshold limits or setting the impurity limits, we need to first know what may be the potential impurity in the particular product. What kind of impurity can exist? So for that, we should have a thorough knowledge on the synthesis of the particular active pharmaceutical ingredient. So the moment we see the synthetic route, we will easily identify what possible impurities which can occur, and at what when are we going to specify those impurities, and how are we going to set the threshold limit. So these are the most important aspects when we are doing the impurity profiling. We should know what would be the potential impurity and what kind of impurities can actually occur, and if is it occurring beyond the threshold limit, should I specify any limit for that impurity? All these things needs to be set before we start with the protocol studies. So actually, these are some of the root causes for the impurities which can occur. So when we are talking about an API manufacturing, the starting material can itself be an impurity, and this API starting material would have been manufactured from something else. So there can also exist some impurities which can pass through. So the starting material can not only lead to the formation of a reaction intermediate, but in addition, they can also lead to the formation of byproducts. Even the impurities which are present in the starting material can also undergo the reaction, and they can also lead to the formation of the byproducts. So these things has to be thoroughly studied. So we use some of the reagents, we use some of the solvents, catalysts. They can also be a reason for the presence of the impurities. The reaction intermediate further gets converted into a final API. During this process, there can be formation of byproducts. Even this intermediate can also exist as an impurity. And the final product is stored until it is converted into a finished pharmaceutical product. So during the storage process, this final API can also undergo degradation degradation because of the various storage conditions maintained. There are chances that they may undergo degradation, and these degradation products can also be a part of an impurity, and the final product is converted into a finished pharmaceutical product, during which we are mixing with the excipients. So when we are doing the excipient compatibility studies, we should also focus on whether any reaction is taking place between the excipient and the API, any interaction is taking place, and is it leading to the formation of a new product. Or sometimes when we do the storage, we should also study the compatibility of the container with that of the active pharmaceutical ingredient. So these are some of the potential sources of impurities, like the residues from the starting material, impurities which are already present in the starting material, residues of the intermediate, some of the byproducts which are formed, some of the degradation products which are formed, the excipient API interactions, interaction products, container API interaction products, some of the solvents what we are using, some of the catalysts what we are using. So all these things can act as an impurity in the final product. So now the very first step in setting up the specifications is that what kind of potential impurities might be present. So a theoretical knowledge on what are the different types of impurities which can form, and what potential impurities may be present in the given API. That is the first step. We need to have all the basic information, and then we need to see whether this drug already exists in the monograph. So normally when we are talking about monograph, in monograph there is a test for related substances. These tests for related substances are carried out for all the pharmaceutical, for each and every pharmaceutical product which is being manufactured as per the Indian Pharmacopoeia. But the related substances which are specified in those monographs are all general related substances. Say for example, when we are talking about paracetamol, there are chances for the presence of 4-aminophenol and 4-chloroacetanilide. 4-aminophenol is an intermediate product, whereas 4-chloroacetanilide is a byproduct which is being generated during the manufacturing of the product. But these impurities, they are in general, but the same paracetamol can be manufactured by different synthetic routes. So when a manufacturer is purchasing a particular active pharmaceutical ingredient from a particular vendor, it is the responsibility of the manufacturer to get the method for analyzing the impurities which were formed in that particular route of synthesis. So each and every API manufacturer should develop a stability indicating analytical method which is capable of separating all the impurities which are formed in their route of synthesis, and they should also give a certificate stating that those impurities are well controlled within the limits, and that has to be rechecked by the finished product manufacturer. And even after during the FR&D process, here also they do certain tests in order to identify any interaction is taking place. So as per ICH guidelines, the organic impurities are basically classified as byproducts, degradation products, intermediates, interaction products, related products, as well as the starting materials. So we should first have a detailed knowledge of how an API is being prepared, what are the various control steps which are used while manufacturing the API in order to control the presence of the starting materials or reaction intermediates or reagents or solvents which are used. And we should also have a knowledge on how an API can undergo degradation, because when we are storing it, there are possibilities that it can undergo degradation. So we should also have a knowledge on how the manufactured API will undergo degradation. In the same way, when we are preparing the formulation also, we should be able to understand what are the various factors which will influence the formation of the impurities or the interaction products, like whether heat is involved, are we going to use water, will water lead to hydrolysis of the drug. So those things. And basically what happens is when we are manufacturing the API, there only we cut off most of the potential impurities. If a particular impurity is formed beyond the specified limit, then the manufacturer identifies few ways. That is, they can change the method of synthesis, or they can identify some new crystallization, recrystallization procedures, so that those potential impurities can completely be removed from the API. And also they carry out the degradation studies for the manufactured API, and they also identify what are the various storage conditions, whether it is temperature and humidity, or it is only humidity, or exposure to moisture, or exposure to some strong acid or an alkali leads to degradation. So they also carry out the degradation studies, subsequent degradation studies for the API, and they try to eliminate those factors of storage conditions. So because of this, they also prescribe the storage conditions when API is being sold to the pharmaceutical manufacturers. So basically, when the researchers work is, the researchers, especially in academia, we work on the impurities which are formed in the pharmaceutical formulations, finished products which are available in the market. So we procure the finished products, we check them whether any additional degradation products are being formed or any API excipients. Even though the industry studies the storage condition, most of the public or most of the wholesalers or the retailers may not maintain the specified storage condition. So under such circumstances, there are chances that the finished pharmaceutical product can undergo degradation, leading to the formation of degradation products or interaction products. So whenever we are working on finished pharmaceutical product, impurity specification only control for API degradation products. We do not focus much on, because most of the impurities which are listed is already controlled. So we focus more only on the degradation products which are used in the active, which are formed from the active pharmaceutical ingredient. So now there is a large focus on control of impurities in the API. So people are now focusing on how to minimize the impurities which are formed in the active pharmaceutical ingredients which are being manufactured. So API impurities in your drug product may be introduced during the manufacturing step, or it could be an API degradation product, or it could be an API reaction by product. So the impurities which are introduced during the manufacturing, they are determined from the detailed manufacturing process description. We all have the BMRs and MFRs, so solvents, reagents, catalysts, residues, starting materials, reaction intermediates used in the manufacturing can be a part of the impurity which are all already controlled. What are degradation products? They are formed because of exposing the drug to extreme stress conditions like accelerated conditions. So there could be certain degradation product which can form when a drug is exposed to extreme conditions, and those degradation products can also be the same as that of the impurities which we have already controlled. So these degradation products are treated as potential impurities. So some of the examples are given here. Chemistry knowledge would be helpful in order to understand the reaction by products. Basically, a chemist can look for areas of functionality, particularly when carbon, oxygen, or carbon, nitrogen, or double bonds are involved. And some of the impurities are specified in the pharmacopoeial monographs as discussed. And there can be formation, the byproducts in the state, in the sense that I wanted only para-aminobenzene. But when manufacturing para-aminobenzene, there are chances that the substitution can take place in the meta position or in the ortho position, or there can be dual substitution, diaminobenzene formation also. So all these ortho, meta substituted as well as the disubstituted products can act as impurities. And the stereochemistry, we all are very much aware of it, because there are a lot of tragedies which had happened in the history because of the stereochemistry. Thalidomide tragedy was one, and now most of the drugs are available in the pure form. Amlodipine, it's available as S-amlodipine. Cetirizine is available as levocetirizine, whereas the counterpart are all having some adverse effects, or they are all very much inert in nature. So why are we focusing more on these impurities as well as on the degradation product? Because as I have already told you, most of the degradation product will have a similar structure to that of the impurity, because degradation is just there are chances that the drug can undergo hydrolysis, and the hydrolysis can lead to the formation of an intermediate which is already used for manufacturing the drug. The further hydrolysis of that intermediate can also lead to the existence of a starting back reaction, can also take place. So that is the reason we are focusing more on the degradation products, because during degradation, new degradation products are formed, but because of the reaction, the impurities, the level of the impurities can also increase. And most of these impurities which are there, they are all having structural alerts for being genotoxic in nature, because in most of the reactions, sulfonic acids are used, and these sulfonic acids, the formation of the sulfonate esters, are all genotoxic in nature. They carry a structural alert for genotoxicity. So according to ICH guideline, any impurity which is routinely observed in a batch data or during a long-term stability trials, when we are carrying out the long-term stability studies, they should be controlled by the specifications. And how the specifications are defined? The specifications are defined based on the, we call it as a permitted daily exposure, PDE, or maximum daily exposure, we call it as. And the threshold for the impurities are defined based on the quantity of the drug which is being consumed by the consumers. So any impurity which is observed below the ICH specification threshold, we need not identify the structure. All those things together can be classified as an unspecified impurity. But if any impurity is above the identification, there are two thresholds which are defined. One is called as the identification threshold. So what is mean by an identification threshold as per an ICH? As per ICH, identification threshold is nothing but a limit beyond which, if a particular impurity exists, then we have to identify what that particular impurity is. Structurally, we have to structurally characterize what that particular impurity is, and we have to establish the safety profile of that particular impurity through in vitro or in vivo studies. What is meant by a quantification threshold? Quantification threshold is nothing but a level beyond which, if a particular impurity is present, then it has to be quantified in all the API batches which are being manufactured or in the finished products which are being manufactured. So they, the ICH defines in two terms, identification threshold as well as the quantification threshold. So impurities above the identification threshold, they have to be identified and they have to be individually specified in the specifications what we are writing for the particular API. So if the maximum daily dose, the identification threshold is 0.1%, whereas if it is greater than 2 grams, then the identification threshold is 0.05% of each impurity. So for a finished product, if it is less than 1 mg, the maximum daily dose is less than 1 mg, 1% is permissible, and if it is greater than 2 grams, 0.1% is permissible. And same way, residual solvents are also being used. As per ICH, the residual solvents are basically classified into 3. Class 1 solvents. These are some of the solvents which has to be completely avoided. That is, they may cause carcinogenic activity and they may also cause environmental hazards. And class 2 solvents, these are some of the solvents which needs to be limited. They are not genotoxic in nature, but they can cause irreversible toxicity like neurotoxicity or teratogenicity. And class 3 solvents are solvents with low toxic potential. That is, the permitted daily exposure is 50 mg or more per day, then we need to specify the limit. They will not cause any health hazards. And class 1 impurity, class 1 solvents, if they are used in the last step, we need to specify how much of that particular solvent is present in the API. So we need to specify. Even class 2 also, if the solvent is used in the last step, it needs to be specified. But if the same solvent is used in the previous steps, that is in the first step of the reaction or second step of the reaction, whereas the third step is the final product, then if it is deducted in the final product, it needs to be specified whether it is within the limit or not. And when it comes to class 2, we have to specify if it is greater than 10% of the ICH limit. And class 3 need not be specified if you exhibit that it is less than 0.5%. And controlling the class 3 solvents is permissible through loss on drying also. So the absence of the specific test should be demonstrated at least for 3 regular production batches and for 6 pilot scale batches. So when we are writing the test specifications for each and every API, all these studies needs to be carried out and all the information has to be provided in the test specifications which is being written. So some of the examples of class 1 solvents, the solvents which needs to be avoided are like benzene, carbon tetrachloride. We all are aware of it, 1,1,1 trichloroethane or 1,2 dichloroethane. Whereas some of the class 2 solvents are acetonitrile, chlorobenzene, chloroform, ethylene glycol, ethoxyethanol, dioxanes, whereas class 3 solvents are all heptanes, isobutyl alcohols, acetic acids, acetone, anisole, butanol, butyl acetate, all these things will come under class 3 solvents. And not only the solvents, metal residues are also important as per ICH Q3. So metal residues, if metal is used as a catalyst either in the last step or in the previous steps, then if it is greater than 30% of the acceptable limit, it needs to be specified. And if it is less than the 30% of the acceptable limit, then non-routine tests are permitted for class 1, class 2, as well as for class 3. Class 3, it is not required to be specified. So what are the class 1 metals? Class 1 metals, platinum, palladium, iridium, rhodium, rubidium, molybdenum, nickel, chromium, vanadium. These are some of the metals which are of significant safety concern. And class 1 metals are classified into class 1A, class 1B, and class 1C as per their permitted 5 parts per million. Whereas in terms of inhalation, it is only 70 nanograms per day. Class 2, the maximum permissible limit is 250 parts per million on oral and 25 on parenteral. Class 3, like ferrous and zinc, which has got minimal safety concerns, are till 130 parts per million. So we have to adopt the stated concentration limits if the dose is less than 10 gram, or we have to set limit for each metal so that it is well within the recommended daily exposure. And even if we are manufacturing the finished product, there also we have to check for the metal contamination. Why? Because the processing involves a lot of equipments, and there are chances that leaching of these metals can also happen in the finished pharmaceutical formulation. So how do we go for setting the limits? So when we are setting the limits, we should understand that the limit what is being set is safe, is qualified to be safe. They should be realistic and they should reflect the batch as well as the stability data of the product which is being manufactured. And an organic impurity above the qualification threshold or the identification threshold has to be properly qualified, and thorough toxicological trial should be carried out. And we can compare the limits which are specified with the International Pharmacopoeia USP or with the Indian Pharmacopoeia for specific impurities. And as I've already told you, most of these pharmacopoeias list only the common impurities which can occur in different synthetic routes. But when we are purchasing from one particular API manufacturer, it can be very, very specific. So all these impurities together should not be more than 0.5% in the final product. So we can compare the levels found in an innovator or a pre-qualified finished product, and we can compare it with our product. That is also one technique of setting the limits. Basically, what an analytical chemist does, or during the manufacturing, what people do is we carry out the stability studies. They carry out the chemical stability studies, and they identify whether the degradation products are formed, and are these degradation products have got a similar structure to that of the impurities which are already established during the API manufacturing. So they are of the chemical stability studies are of great concern, because they affect the quality, safety, as well as the efficacy of the drug product. And changes when we are storing the product for a longer period, there are changes that that can risk the patient's safety because of the formation of a toxic degradant product. Because of this, the dose level can also decrease. Thus, stability study is a vital part in any drug development program, and it is compulsory that we should conduct the stability programs during the drug development when we are developing a new formulation or when we are developing a new drug. And for drug substance stability, we have to establish the retest period. That is, we are establishing the shelf life. For product stability, we are also establishing the shelf life, and we are also establishing the storage conditions, the required storage conditions. So all these stability studies should be supported by a potent analytical method. And this analytical method should be so precise that it can quantify the particular active pharmaceutical ingredient in the formulation, and it can simultaneously separate all the degradation products or all the a common term is used, which we call it as a related substance. So related substance can either be an intermediate, or it can be a byproduct, it can be a starting material, or it can be a degradation product. So all these are related to the structure of the drug. So that's why we call it as a related substance. So to separate the related substance also, stable method. So these assay methods, what we develop, either we use an HPLC, we develop a HPLC method, or we develop LC-MSMS method. So these methods are called as stability indicating analytical methods, and all these stability indicating analytical methods are validated as per the ICH Q2 guidelines, Q2A, R2, Q2B. Now we have a revised, the second revised copy, and these methods are applicable for potency assay because they should be capable of detecting the degradation, that is the disappearance of the drug, and they should also be capable of detecting the related substances for detecting as well as quantifying their appearance as well as the growth of these related substances during the degradation studies. So for this purpose, forced degradation or stress degradation studies are designed. We call it as the stability studies. They are designed to provide the information. So all these degradation conditions are very much specified in ICH Q1 guidelines, International Conference of Harmonization, Council of Harmonization, Q1 guidelines, quality guidelines. So quality guidelines talks about the stability testing of new drug substances as well as the drug products. So for carrying out the stability studies, stress testing is used. So what we are doing here, we are exposing it to intrinsic stress conditions, and we try to identify the likely degradation products which can help us to understand the degradation pathway as well as the intrinsic stability of the molecule. Then we use those stability study samples to develop an stability indicating analytical method, and then we use it for further potency assay as well as the assessment of the related substances in that particular active pharmaceutical ingredient. So as per ICH, it is being carried out. These stress tests or intrinsic stability studies are being carried out on a single batch of the drug substance which is manufactured in the industry, and it includes studying the stability of the drug in under different temperature conditions. Like the temperature is increased at 10-degree increments, and we study what are the various degradation products, how the drug is undergoing degradation under various humidity conditions like 60% RH, 75% RH, or even greater. Also by exposing the drug to oxidative stress as well as photolytic studies. And this test also helps us to evaluate the susceptibility of the drug substance to hydrolysis, because when we are carrying out the manufacturing, the drug may get into a finished product, the drug may get exposed to a wide range of pH values. When you are converting it into a solution or suspension, even for carrying out an analytical study, the drug will be exposed to different pH conditions if you want to develop an analytical method, or we are doing a dissolution study. So we should also study the intrinsic stability of the drug under wide pH ranges. And photostability is also an integral part, because during storage, they may be exposed to extreme temperatures, especially light. So that also can have an impact. And when are we going to perform all these forced degradation studies? During pre-investigational drug development. So when the investigational new drug, when we have identified a new drug, and So when we have identified a new drug during the pre-IND stage, we do the force degradation studies, and during the formulation stage also we do the force degradation studies. We check the stability indicating quality attributes. We also perform the degradation studies, and for preclinical studies also we check whether the degradants are having any toxicity impact. We also identify whether these degradation products or these impurities are toxic. And also during clinical development, we compare the preclinical to the clinical quality, and we check whether these impurities or these degradation products are having any influence. And we also compare the pre to the post manufacturing changes, and we also do the stability studies. Post marketing, this is what most of the analytical chemists carry out. Identify new stress conditions, because once it enters into the market, during the manufacturing step there can be new stress conditions which were developed. There can be chances that we are changing the manufacturing process, or there can be additional indications which needs to be defined for that drug. So once the drug enters into the market, also stress degradation studies are being carried out for the API as well as for the finished pharmaceutical products. And what are we going to force degrade? The drug substance. We are going to study the rate at which the degradation takes place. For the drug product also, to check whether there is deviation on the intended storage conditions, and even in the final drug product, that is it compatible with the final package? Is it compatible with the APIs which are, excipients which are being used? And when we are going for reconstitution with water or reconstitution with some other solvent, is it compatible there? Or is it compatible with the packaging material what is being used? And what are the different types of force degradation studies which are carried out? One is thermal study. We can expose it directly to temperature, different temperatures. We can keep it in hotter oven. We can study. We can increase the temperatures, like 10 degrees Celsius increments can be given, and we study whether the drug is undergoing degradation under various temperatures. We can expose it to different humidity conditions. We can do acid-base hydrolysis, which is nothing but studying the intrinsic stability of the drug under a wide range of pH, oxidative stress, photolysis, exposing it to UV radiation, freeze the cycles, because some of the drugs may be stored under a frozen condition. So before using, we thaw it and use it. And we can expose the drug to shear conditions like shaking or pump filling or some other pressurized conditions, and we can check whether the drug is undergoing degradation or not. Because these shear conditions, studying the degradation pattern under shear conditions is very, very important when we go for manufacturing the manufacturing the drug product. And these should be driven by the stability profile of the product, chemical stability as well as physical stability. So the chemical stability involves hydrolysis, deamidation, isomerization, oxidation, disulfide exchange, beta elimination, whereas the physical stability talks about the conformational stability, denaturation, absorption, aggregation, and self-association. And why force degradation studies are required? Because these degradation products can also cause various health and safety. They can impact the health and the safety of the patient. They may cause adverse effects. They may produce genotoxic effects. Nitrosamine is one example, which is an impurity which is formed during the manufacturing process. And lot of studies are being carried out on different types of nitrosamines which can exist in the different types of formulations. So which is also a safety concern, which can lead to carcinogenicity and genetic mutations. And if we are controlling, as I've already told you, most of the degradation products can have can be a impurity which is already existing. So if the API is being stored for a longer period of time under abnormal conditions, then automatically the level of the impurity can increase. So controlling the degradation related impurities is also possible by carrying out the degradation studies. We can identify the it involves the identification of the potential degradants which are found during the study in either the drug substance or the drug product under long-term or accelerated storage conditions, and you can select appropriate measures to minimize those impurities in the final product. And their identification and characterization are the two key steps, because you need to know which is the degradation product which is very similar to the impurity, and how much quantity of that is formed. So for that, we go for doing the stress degradation studies. So these degradants or impurities should be controlled well below 0.1% if they are genotoxic in nature. And regulatory requirement states that whenever we are submitting the documents for approval of an IND or an NDA or an ANDA, then we should also submit the following data. So what are the possible degradants which are formed, what are their structures, what is the degradation pathway, and what is the intrinsic stability data of the particular drug, and also a validated stability indicating analytical procedure to separate these degradants as well as to quantify these degradants. So some of the following issues are addressed in the regulatory guidelines. Force degradation studies are typically carried out using one batch of the material, and they should be more severe than the accelerated stability testing. Photostability should be carried out, which is an integral part of the forced degradation study design. And degradation products which is not formed in the accelerated or long-term stability, they need not be isolated or characterized, and mass balance has to be compulsorily considered. Carrying out the mass balance issues. And some of the issues are not addressed in the regulatory conditions. They say that it should be more intrinsic than the accelerated stability studies. But what is the exact experimental conditions? Even ICH guideline doesn't define. So the experimental design is left to the applicant's discretion. ICH states that when we are carrying out the forced degradation studies, we need to expose it to different temperature. We need to carry out the study under different time periods, like 24 hours at room temperature, 48 hours at room temperature, 1 week at room temperature. But they do not specify that you should compulsorily carry it out for 1 week or for only 48 days. And the experimental design is left to the applicant's discretion. So what kind of experimental design we are going to do, that is left only to the applicant's discretion. And this is the flow chart. First, we try to predict the degradant, because there are a lot of databases which are available, softwares which are available, and basic chemical knowledge, seeing the structure, we will be able to tell that these may be the possible degradants. Then we decide protocol to carry out the forced degradation studies depending on the chemistry of the drug as well as the regulatory guidelines. Then we perform the experiments. We design our own experiments because regulatory guidelines, ICH, do not specify these are the conditions. So we design our own guidelines and we set the appropriate sample points for the appropriate stress conditions. Then we perform the screening of the degraded samples. Like you challenge the analytical methodology. You develop a new HPLC or we develop a new LC-MS methodology, and we try to see that all the degradation products are completely separated from the drug as well as from the already specified impurities. And then you evaluate the peak purity or you evaluate the potency of the main active pharmaceutical ingredient by using a diode array detectors or by using LC-MS technique. And then if a degradation product is formed in a major quantity, then we determine the structure of that particular degradant. We isolate it by using a semi-preparative or a preparative HPLC technique, and then we subject it to LC-MS or LC-MS analysis, NMR analysis, and we try to elucidate the structure of those degradants. And after elucidating the structure, we report those structures, and we also elucidate the pathway and share it on the database, so that publish it, so that the data is available to the public for ready reference. So predicting the degradants, we can use in silico or based on the chemical knowledge. There are some of the softwares which are available. Cameo, Delphi, and Zenith are some of the softwares. And based on the chemical knowledge, like chemistry knowledge, based on the published literature or the major mechanisms of chemical decompositions, which we are aware of based on their functional groups, then we design the protocol. So protocol is what are we going to study? Are we going to work on the finished drug product, or we are going to work on the active pharmaceutical ingredient? Are we going to work on a solid state or a liquid state? So in both the states we are supposed to work. And then development of a stability indicating analytical method, and you have to set your stress conditions in such a way that only 5 to 20% of your API undergoes degradation. Because if 100% degradation, say for example, I wanted to do it for oxidative stress, under oxidative stress conditions, I wanted to do the study. So initially when I start with 30% of hydrogen peroxide, and I keep it under room temperature for 24 to 48 hours. After 48 hours, I assess the stability of the sample. If the sample is more than 90% stable, it is not undergoing any degradation, 95% it is stable, then I increase the intensity of my forced degradation studies. Like for example, instead of carrying it out under room temperature, I do it with what we call under heat, like 40 degrees. I reflex it at 40 degrees Celsius, and I withdraw the sample at different time intervals, and I check whether the degradation is between 5 to 20%. So this is how the initial trials are carried out. Either it be an acid hydrolysis or a base hydrolysis, or under neutral pH, or with oxidative stress we are conducting. So preliminary experiments are being carried out, and then we finalize that these are the stress conditions under which the drug is undergoing only 5 to 20% degradation, and that is included in the protocol. So these stressed samples should be compared with the unstressed, that is the freshly prepared drug, as well as with the appropriate blank. And these are some of the typical stress conditions. For hydrolysis, we use from 0.01 normal to 1 normal hydrochloric acid or sodium hydroxide, depending on the type of the pH we require. This is mainly carried out under liquid state for API. And for drug product, in most of the cases, we do not do this. Oxidative stress is carried out for API as well as for the drug product. Between 0.3 to max, we go till 30% of hydrogen peroxide. Light, it is 120 lux hours exposed for a period of 7 days. Temperature, we study the temperature from 10 degree till 70 degrees. We increase at 10 degrees, at 20, at 30, at 40 till 70 degrees in an oven. We do the study. It is done for solid state as well as for the liquid state. And temperature and humidity, again, we vary the temperature and simultaneously we vary the relative humidity also. And then we study the intrinsic stability of the particular drug. And this is some of the typical means we call it as an optimized stress study design. So for an API, the study is being carried out between 1 to 7 days. And under temperature and humidity, it is carried out up to 2 weeks. Whereas for a drug product, it is carried out till 48 hours. For temperature and humidity, it is up to 3 weeks. And then, as I've already told, if the drug is not undergoing any degradation at room temperature, even after 48 hours, then we go for increasing the temperature. Like we add 0.1 hydrochloric acid in order to initiate acid hydrolysis, and then we reflux it at 40 degrees Celsius for a period of 48 hours. And intrinsic means you increase the stress conditions. So 40 degrees, 50 degrees, and 60 degrees we study. Even after, that is, the study starts like this. I first do it at room temperature. If the drug is not undergoing any degradation, then I expose it to severe stress conditions. Like I reflux it at 40 degrees with 0.1 N HCl, or with 0.01 N, or with 1 N, whichever is the strongest, if the drug is stable. To get at least 20% of the drug degraded, to identify the structure of those degradation products. So sometimes the reflex is even carried out till 5 days if the drug is so stable. So sampling can be done on the first, third, as well as the 5th day. So pH, under what pH we study 2, 4, 6, and 8, the body conditions. And hydrogen peroxide, either we do 3% hydrogen peroxide or 30%, 6% hydrogen peroxide. And one more oxidative stress reagent which is used is azo-bis isobutyronitride. That is also an oxidative stress reagent which is used. Light, we are exposing it to 1200 lux power, UV radiation, and thermal is heating chamber along with the humidity. And humidity studies and light studies are carried out for a minimum period of 2 weeks. And then we go for developing the stability indicating analytical method. So the method should accurately quantify the active ingredient without interference from the degradation products as well as from the process impurities. And there should be a proactive approach when we are developing the SIAM. That is, you do the forced degradation at the early stage of the development, identify the key degradation products, and then use it in the method development process. And sometimes if forced degradation studies are performed early, method development and identification of the primary degradation products and unknown impurities can be performed simultaneously. And these are some of the general steps. First, critical study of the drug substance to understand the degradation route, collect the information on the physicochemical properties of the drug, as well as the theoretical degradation products what we have designed, carry out the forced degradation studies, perform the preliminary separation, optimization of the chromatographic condition is itself carried out with the stressed samples. Then the final method is optimized for various parameters like the column to be used, the mobile phase ratio, pH of the mobile phase, flow rate, the deduction wavelength. 2 types of deductors are basically used here if we are working with HPLC, because most of the compounds are not UV sensitive compounds. So the degradation studies, if we are using HPLC, the degradation studies are carried out in UV detector or in a PDA detector. Along with that, we also go for using a bulk property detector, which is nothing but a refractive index detector. So some of the compounds, some of the degradants which are non-chromophoric in nature can be detected by the use of the refractive index detector. So we optimize the several parameters which are involved in the method development and come up with the final chromatographic condition. So it can either be a gradient HPLC or it can be a isocratic HPLC condition, depending on the type of the number of the degradation products which are formed. Then we identify and characterize the degradation products. Then we try to synthesize those degradation products. And from there, we prepare the standards. And then we go for validating the method. So I want to stress that most of the cases when we are doing the stability indicating analytical method, they develop an analytical method and then they carry out the stress degradation studies. It is the other way around. So we have to first carry out the stress degradation studies and then only we have to go for developing the analytical method. And using only a PDA or UV detector is not sufficient, wherein we should also go for using a non-chromophoric detector which can detect non-chromophoric compounds. So LC-MS or LC-MS plays a major role because it minimizes most of the steps when we are going for using an LC. Coupled with an mass spectrometry, the previous session would have been on LC-MS. So when we are using such LC coupled with MS, it gives us a lot of information. One is optimizing the method we do. Then we try to identify all the degradants which are formed. Simultaneously, we will get the molecular mass. And also, if we have an MS, then we will also get the fragmentation pattern with which we can elucidate the structure of the degradants. So once the method is validated, we assess the mass balance. We evaluate the purity or the potency of the active pharmaceutical ingredient. So mass balance is defined as adding together the assay value and the levels of the degradation product to see how closely they are adding up to 100% of the initial value with very, very marginal analytical error. So they give us information assuring that the analytical method is capable of controlling all the significant degradants, and it is capable of specifying and quantifying the API even in the presence of the degradants as well as the process impurities. And the integrity of these analytical peaks are verified by using LC-MS in a selective ion monitoring mode or by recording the PDA chromatogram to establish the peak purity. So the key degradation sample sets includes significant degradants, process impurities, which includes the intermediate starting materials and byproducts. I'm not stopping only with the degradation studies, but when I'm developing the SIAM, I'm also using the process, the impurities which are already specified in the API. So process-related impurities and known degradants sometimes are available as RS, which can be used. Unknown degradants, they are very, very critical in the development of stability indicating analytical method. And they can, when we are carrying out the forced degradation studies, they may generate complex mixtures of degradants, but method development is very, very important. When we are talking about a chiral drug, the other counterpart of the main active ingredient should also be considered as a degradant or as an impurity, and it should be used for developing the analytical method. Identifying the degradants, first step is to enrich the degradant and then separate it. Can go for thin layer chromatography or solid phase extraction or accelerated solvent extraction, pressure liquid extraction or preparative chromatography, HPLC, or supercritical fluid chromatography. Identification, we can isolate, we can recrystallize it, we can send it for NMR, IR, MS, or we can directly subject it to LC MS studies or LC NMR studies for the degradants can be identified. And then the structure searchable degradation profile database is prepared and it is shared globally. And this data will help in establishing a proactive approach to drug stability, which can predict problems and identify trends in the data. So the following slides will have few of the examples of the studies which has been carried out in our laboratory. This is one study. We have carried out the degradation of the antiretroviral drug Darunavir. Under oxidative stress condition, it led to a formation of one degradation product, which was isolated by using after 15 days at room temperature by using 30% intrinsic degradation condition. So at 12 minutes, the degradant was formed and the pathway and the structure was elucidated. So this was the structure of the oxidative degradation product with an MBIZ of 574. We have subjected that solution to LCMS. We have determined the MBIZ value, the molecular ion, and then we defined the structure. This was a possible pathway. And this is one more drug, R-modafinil, and some of the chromatographic conditions. And under basic condition, this drug had undergone degradation. We have subjected the drug to acid hydrolysis, like 1 molar hydrochloric acid at room temperature for 24 hours, 0.1 molar sodium hydroxide, because it is very susceptible to base, and 6% hydrogen peroxide and sunlight for photodegradation. And under basic conditions, it underwent degradation, and this was the degradation product, and that was isolated and structurally characterized. So this was the degradation pathway which was defined. And this was another drug, levosulfuride, which was studied in the laboratory. And again, here also oxidative degradation product, which was isolated, and the degradation pathway was defined. So these are all oxidative stress conditions, and this was the drug, and this was the degradant which was formed, and the degradation pathway which was defined for the drug product. And this is one for the coloring reagent tartrazine. This was also an oxidative degradation product. So, and the degradation pathway was elucidated. This was the structure of the oxidative degradant which was elucidated. And this is one study which was carried out for characterization of the degradation product. I think this is for raltegravir, an antiretroviral drug. And this was the degradation pathway of the drug as such based on the MS as well as the MS data. We have gone for identification. And We have also gone for identifying the degradation products. DP2, we were able to isolate 7 degradation products. We have recorded the MS as well as the MSMS spectra of all the 7 degradation products. And then we have elucidated the structure of all the 7 degradation products. And out of the 7 degradation products, DP3, DP4 are all existing impurities. They are already existing in the market as an impurity. So subjecting the drug to intrinsic stress condition led to the formation of these degradation products as well. And thank you very much, everyone, for your patient listening. And apart from this, even for some of the coloring agents in food, a few of the studies in our laboratory which were carried out for some of the coloring agents which are used in day-to-day food. And these coloring reagents are having a tendency to react with some of the excipients which are used in manufacturing these foods, citric acid in certain cases, juices and all which are being prepared, the citrus juice, fruits when they are preparing the citrus flavored fruit juices, these coloring reagents are interacting with those citrus fruit juices, the citric acid which is present, and they are leading to the formation of new degradation products. So some of the studies apart from this, even for antidiabetic drugs also, antidiabetic drugs, anti-cancer drugs also, degradation studies were carried out. Thank you. So the session is open for questions and discussions, if any.
Thank you, madam. Thank you
madam,
so much.
Sorry for the interruption. Anita, madam, I'll take care of. Hi. Madam, thank you very much. The part of talk today is very insightful about the degradation product as well as the impurities. And first of all, I have 2 questions, madam, in that. One is, you already quoted that about the nitrosamines.
Yes, sir.
Because of this, the serious issue only, the FDA has given the guideline as well as the ICH M7 guideline also came out, R2. And my question is, normally the degraded or impurity products are in nanogram level.
Yes, sir.
To identify or to characterize which particular method of analysis is feasible, or it is easy to get a clear-cut idea about a particular impurity, madam.
Sir, I see MSMS is very good, sir. If we are directly working with the API, for example, if we are procuring the API and we are working on identifying the impurities, process-related impurities.
Okay.
And LC-MSMS is very good, where we can go for nanogram as well as the phenitogram quantities.
Yes,
but if we are working on forced degradation studies, suppose already the drug is available in the market, so I just wanted to study the intrinsic stability of the drug API or the pharmaceutical formulation. Then we have methods of enrichment. That is, instead of using if 0.1 normal hydrochloric acid acid hydrolysis, by using 0.1 normal is generating only 10% degradation, I can intensify the condition. I can go for 0.5 normal, or I can go for 1 normal. I can intensify the condition so that the quantity of the degradant increases, and there I can go for using a HPLC method, sir.
Okay. Thank you, madam. And another question. Here, the guidelines only will take care of the known impurities.
Yes, sir.
Whereas if the unknown impurities, how we are going to give the data about the impurity profile, madam, for a new, either investigational new drug or even the new drug development. If it is the impurity is unknown one, it is a new one, so that we are not able to have the standard one, right, to compare.
Yes, sir.
Or to characterize. So
yes.
In that case, what we will do, madam?
Sir, actually, ICH specifies that if one particular impurity is beyond the threshold limit, that is 0.5%, then only when we are preparing the regulatory documents, we have to isolate that impurity, we have to structurally characterize it, and we have to establish the safety data. Otherwise, when we are doing the mass balance study, we are doing, no, sir, we are balancing the mass. So when we are balancing the mass, overall, all impurities should be equivalent to 100%. That is your API, identified impurity, unidentified impurity, everything, if it is equivalent to 100%, if it is matching the mass balance, it is not required for us to structurally characterize the unidentified, that is the impurities which are formed in very, very, very small quantities, sir, as per the guideline.
Yes,
Yeah,
yes.
so the regulatory documentation is also not required for that. But out of interest, we can go for identifying. Enrichment we can do, sir. Like instead of taking 10 mg and carrying out the impurity profiling studies, we can take bulk quantities.
Okay.
So we can enrich that particular impurity and then we can go for isolation and characterization if required. Or we can do some of the these degradation studies. So when we are doing the degradation studies, that itself will enrich those unidentified impurities to a certain extent.
Okay.
So that is also one method of doing it.
Okay. One more question, madam.
Yes, sir.
The question is,
so there is one question in the chat box also.